You could build the most advanced spacecraft ever conceived, travel for 1,000 years in a perfectly straight line, and still have absolutely no idea where you are. Not because you made a mistake, but because the universe was never built for navigation. It was built for expansion. And if home is nothing but a pale dot lost in an ocean of 2 trillion galaxies, what would it actually take to find your way back? If you're someone who wants to feel that sense of cosmic wonder on a regular basis, please subscribe to the channel. Now let's get started. When you leave Earth's immediate neighborhood, the GPS satellites are a tiny cluster of metal, and even the sun begins to shrink into insignificance. Here's a number that tends to stop people cold. At a distance of just 1 light-year from our solar system, and 1 light-year is approximately 9.5 trillion kilometers, our sun would appear to the naked eye as simply another bright point of light in the sky. Not special, not obviously different from the hundreds of billions of other stars in the Milky Way. You could look directly at it and have no idea you were looking at home. This isn't a thought experiment designed to make you feel small, though it might do that too. This is a real operational challenge that space agencies have studied in depth. The Deep Space Network, a genuinely extraordinary system of enormous radio dish antennas positioned at 3 locations around the globe, in Goldstone in California, near Madrid in Spain, and outside Canberra in Australia, is the most sophisticated deep space communication and tracking system humanity has ever built. It is the invisible thread connecting us to every robotic spacecraft we've ever sent beyond Earth's orbit, and it works beautifully right up to the edge of what physics will allow. Consider Voyager 1, launched back in 1977. Now over 45 years into its journey, it is the farthest human-made object that has ever existed. As of the most recent measurements, Voyager 1 is more than 23 billion kilometers from Earth. That is a distance almost impossible to visualize, and yet we can still track it, just barely. Radio signals traveling at the speed of light take more than 21 hours to make a one-way trip between Voyager 1 and our antennas on Earth. 21 hours, one way, to something still inside our own solar neighborhood, cosmically speaking. Now scale that up. The nearest star system beyond our own is the Alpha Centauri system, sitting at a distance of approximately 4.24 light-years. To send a radio signal there and receive a reply would take more than 8 years, assuming, of course, there was something there to send one back, and that's just the nearest star. The Milky Way galaxy is roughly 100,000 light-years across. The nearest large galaxy to ours, the Andromeda Galaxy, is about 2.5 million light-years away. The observable universe, the bubble of space we can actually see with our most powerful instruments, stretches out to approximately 46 billion light-years in every direction. At those distances, the concept of sending a signal to ask where you are doesn't just become slow, it becomes meaningless. By the time any response could reach you, the civilization that sent it might not exist anymore. The star it came from might have already died. Time itself becomes part of the navigation problem, and we haven't even gotten to the really strange part yet. Here's something that most people, even science enthusiasts, don't fully sit with. The universe is not standing still, and that's not just a poetic way of saying things are moving around. What I mean is that space itself, the fabric of reality that everything exists inside of, is actively expanding. Right now, in every direction, at every scale. This discovery, one of the most profound in the history of human knowledge, was published in 1929 by an astronomer named Edwin Hubble, working with observations made using the Hooker telescope at Mount Wilson Observatory in California, which was at that time the most powerful telescope on Earth. Hubble demonstrated something that almost nobody was prepared for. Galaxies beyond our own Milky Way were moving away from us, not just a handful of them on one side of the sky, all of them in every direction. And the farther away a galaxy was, the faster it appeared to be receding. The implication was staggering. The universe wasn't static, it was growing. And it had been growing since the very beginning, since the Big Bang, approximately 13.8 billion years ago, when all of space, time, matter, and energy erupted outward from an extraordinarily hot, dense state and began the long, slow, ongoing process of expansion that continues to this day. Now, what does an expanding universe have to do with finding your way home? It has everything to do with it. Think of it this way. Imagine you mark a point on a balloon with a felt tip pen and you call that point home. Then you start inflating the balloon. The mark doesn't move, but every other point on the balloon moves away from it. And from the perspective of any other mark anywhere on the balloon, all of the other marks are moving away too. There is no center of the balloon's surface. Every point looks like it's at the middle of the expansion. Every point sees everything else retreating. That is, with important caveats, roughly analogous to what's happening in the universe. And one of those caveats makes the navigation problem even harder. In the real universe, it isn't that galaxies are flying through space away from each other. It's that space itself is growing between them. The distance is increasing not because anything is traveling, but because the medium those things exist in is stretching. This means there is no fixed coordinate system for the universe. There is no cosmic grid, no origin point, no 0, 0, 0 from which all other locations can be measured. Every location in the universe is equally valid as a reference point, and every location sees every other location moving away from it. You cannot drop an anchor in an expanding universe. You cannot say, I am at position X in any absolute sense, because position X is itself moving relative to everything else, which is itself moving in a universe with no fixed frame of reference. The Planck Space Telescope, a European Space Agency mission that operated from 2009 to 2013, gave humanity its most detailed portrait ever of the cosmic microwave background radiation. This faint glow, a remnant of heat left over from the Big Bang itself, is detectable in every direction across the sky. The Planck data confirmed that on the very largest scales, the universe is remarkably uniform. The temperature of this background radiation varies by only tiny fractions of a degree from one patch of sky to another. That uniformity sounds reassuring. It sounds like order, but for a navigator lost in deep space, it is the opposite of reassuring, because when everything looks the same in every direction, when there are no obvious landmarks, no asymmetries, no giant neon signs pointing toward the Milky Way, how do you know which way is home? And that question, as it turns out, opens a door into something even deeper, something that cuts right to the heart of how space and time actually work. Because here's what your intuition tells you: space is a big empty stage, and objects move across it. Simple, logical, wrong. Space is not a passive backdrop. Space is a dynamic physical structure. It curves, it bends, it stretches and compresses. And those curves are not just mathematical curiosities. They are the very reason why gravity exists, why light bends around massive objects, and why a straight line in deep space is not the same thing as a straight line you could draw with a ruler. We're going to get deep into that in just a moment, but I want you to hold on to this feeling right now, this sense of the ground shifting beneath you, because that's exactly what the universe is doing. It is shifting the ground, constantly, in every direction. And the further you go from everything you know, the more you feel it. What happens when you try to plot a course through a universe that curves back on itself? What happens when the very light you'd use to navigate has been traveling for so long that the source that emitted it no longer exists? What happens when your instruments are measuring a past that no longer reflects the present? Stay with me, we're just getting started. Let's talk about light for a moment, because light is everything when it comes to how we understand the universe. every photograph ever taken by every telescope ever built. From the earliest glass lenses pointed at the moon to the James Webb Space Telescope floating serenely at a distance of 1.5 million kilometers from Earth, every single one of those images is made of light, photons, tiny packets of electromagnetic energy traveling at just under 300,000 kilometers per second, the absolute speed limit of the universe. Light is the messenger. Light is the medium. Light is the only currency in which the cosmos pays out information. And here is the part that should make you stop and sit very still for a second. You have never seen the universe as it actually is right now. Not once, not ever. Every photon that has ever landed on your retina, every signal that has ever been captured by a radio dish or an orbiting telescope is old. Some of it is very old. Some of it is ancient beyond any meaningful human scale. Because light, fast as it is, takes time to travel, and across the distances of the cosmos, that travel time becomes something enormous. Something that fundamentally changes what it means to see something. When you look at the moon, you're seeing it as it was about 1.3 seconds ago. Harmless enough. When you look at the sun, you're looking roughly 8 minutes into the past. Still manageable. When you look at Mars at its farthest point from Earth, the image you're seeing is about 22 minutes old. But when you look at the Andromeda Galaxy with your naked eye on a clear, dark night, and you can see it, just barely, as a faint smudge near the constellation Perseus, you are looking at light that left its source approximately 2.5 million years ago. 2.5 million years ago, our ancestors on Earth were early members of the genus Homo, making stone tools on the African savanna with no concept of galaxies, telescopes, or the speed of light. And the photons you're catching with your eyes tonight left Andromeda when those people were alive. Now push that further. The James Webb Space Telescope, which began science operations in 2022 and represents perhaps the most extraordinary leap in observational astronomy since Hubble, has captured light from galaxies so distant that the photons composing those images have been traveling for over 13 billion years. We are looking at objects as they existed when the universe was less than 1 billion years old, less than 7% of its current age. Those galaxies, whatever they look like today, if they even still exist as recognizable structures, we have absolutely no way of knowing. We are seeing their past, their ancient, unrecoverable past. And this is precisely why light, magnificent and irreplaceable as it is, becomes deeply problematic as a navigation tool in deep space. Because when you navigate, you need to know where things are now, not where they were millions or billions of years ago. If you're trying to find your way home and you can only see where home was 13 billion years ago, you have a problem that no amount of computing power can fully solve. The information you need simply doesn't exist yet. It hasn't arrived. This is where things get philosophically rich. And I want you to really feel the weight of this idea. In everyday life, seeing and knowing feel like the same thing. You look at a chair across the room and you know it's there. The light from the chair reaches your eyes in such a tiny fraction of a second that the delay is completely irrelevant. Seeing and knowing are effectively simultaneous, but the universe, operating on scales that make your living room look like a subatomic particle, ruthlessly separates those two things. Seeing and knowing become entirely different operations, and the gap between them is filled with uncertainty, with elapsed time, with change that may be impossible to account for. Imagine you're aboard a spacecraft that has somehow traveled to a region of space several million light-years from the Milky Way. You look back, trying to find home. The light reaching your instruments from the Milky Way is millions of years old. The galaxy you're looking at, that beautiful, familiar spiral, is not the galaxy that exists right now. Stars have been born and died in the time that light has been traveling toward you, The positions of every object within it have shifted. Even if you could plot a precise course toward the source of that ancient light, you wouldn't be heading toward home as it is. You'd be heading toward a ghost, a memory encoded in photons. Now add to this the expansion of the universe we talked about in part 1. Not only is the light old, but the source of that light has been moving away from you the entire time the light was in transit. The Milky Way you're looking at appears to be at a certain distance, but the actual current distance of the Milky Way is greater. Because while those photons were crossing the void, space itself was stretching beneath them, pushing everything further apart. So your instruments give you one number, but reality offers a different, larger one, and calculating the difference requires knowing the precise rate of expansion, which itself turns out to be one of the most hotly debated numbers in modern cosmology. This debate has a name. Scientists call it the Hubble tension, and it is currently one of the most exciting unresolved problems in all of physics. Here's the issue. There are two primary ways to measure how fast the universe is expanding: a value known as the Hubble constant, measured in kilometers per second per megaparsec, which is a unit of cosmic distance equal to roughly 3.3 million light-years. One method looks at the cosmic microwave background, that ancient afterglow of the Big Bang that the Planck telescope mapped so exquisitely, and uses the physics of the early universe to calculate what the expansion rate should be. That method gives a value of approximately 67.4 kilometers per second per megaparsec. The other method uses nearby distance markers called Cepheid variable stars and type Ia supernovae, stellar explosions of known brightness that act as standard candles across cosmic distances to measure the expansion rate directly. That method consistently gives a value of around 73 kilometers per second per megaparsec. Those two numbers should be the same. They're measuring the same thing. And they are not the same. The gap between them is small in absolute terms, but it is statistically significant, and it has refused to go away despite decades of increasingly precise measurements. Either one of our measurement methods has a subtle error we haven't identified, or the standard model of cosmology, the framework we use to describe the universe's history and structure, is missing something important, something big, and right now nobody knows which it is. For a navigator in deep space, this isn't just an academic puzzle. It means that even our best theoretical models of the universe, the ones that would underpin any deep space navigation system, carry a built-in uncertainty about the fundamental rate at which the fabric of reality is expanding beneath you. You are trying to plot a course on a map whose scale is still being argued about. Now let's talk about something that, on the surface, sounds like a solution. And in many ways it is a genuinely brilliant one, but it has limits that reveal just how stubborn this problem really is. Pulsars. If you haven't encountered pulsars before, you're about to meet one of the most extraordinary objects in the known universe. A pulsar is a type of neutron star, the collapsed core of a massive star that has exploded as a supernova. When a star between roughly 8 and 20 solar masses reaches the end of its fuel supply, it can no longer support itself against gravity, and it collapses catastrophically. The outer layers are blasted away in an enormous explosion. The inner core is crushed together so violently that protons and electrons are forced to merge into neutrons, producing a sphere of almost pure neutron matter, roughly 20 to 25 kilometers across, but containing more mass than our entire Sun. Let that sit for a moment. Something heavier than the Sun, squeezed into a ball the size of a mid-sized city. The density of a neutron star is so extreme that a single teaspoon of its material would weigh approximately 400 million tons on Earth. You could take a teaspoon from a neutron star, and if you dropped it on Earth's surface, the force would be almost incomprehensible. And pulsars spin. They spin incredibly fast, some of them completing hundreds of rotations every single second, and as they spin, they emit beams of electromagnetic radiation, particularly radio waves, from their magnetic poles. These beams sweep across space like the beam of a lighthouse, and because the physics governing the spin of a neutron star are extraordinarily stable, the pulses arrive with a regularity that rivals the most precise atomic clocks we have ever built on Earth. This extraordinary precision is what makes pulsars interesting as a navigation tool. If you know the exact position and timing characteristics of several pulsars distributed across the sky, you can, in principle, use the arrival times of their pulses at your spacecraft to triangulate your position in three-dimensional space. The idea is elegant. The pulsars are essentially a natural GPS network, broadcasting their signals continuously across the galaxy, free of charge, powered by the leftover spin energy of stellar collapse. NASA has taken this idea seriously, very seriously. An experiment called NISA, the Neutron Star Interior Composition Explorer, has been operating aboard the International Space Station since 2017. One of its goals is to demonstrate pulsar-based navigation using observations of X-ray pulsars to determine position in space. In 2018, NISA achieved a significant milestone. It demonstrated that pulsar timing could be used to determine a spacecraft's position to within roughly 5 kilometers. That is a genuinely impressive result for a first-generation demonstration. But here is where the limits start to appear. And I want to walk through them carefully because each one reveals something deeper about the nature of the universe. First, pulsars slow down. They are not perfectly stable over extremely long timescales. As a pulsar radiates energy, it loses rotational momentum, and its spin gradually decreases. This slowdown is incredibly slow. We're talking about changes that accumulate over thousands or millions of years, but in the context of a civilization that might need navigational references lasting millions of years, it matters. Some pulsars also experience sudden speed-up events called glitches, where the rotation rate abruptly increases for reasons that are still not completely understood. These glitches introduce timing irregularities that would need to be accounted for in any navigation system. Second, pulsars are distributed unevenly across the galaxy. They tend to cluster along the galactic plane, in the regions where massive star formation and supernova events are most common. If you're navigating within the Milky Way, this distribution might be workable. You can observe multiple pulsars spread across a reasonable portion of the sky. But if you're in intergalactic space, far from the galactic plane, your view of the available pulsars is dramatically reduced. The signals become weaker with distance, and the geometry of triangulation becomes less reliable. Third, and this is the one that really drives the problem home, pulsar navigation, like all navigation methods, requires you to already know something. Specifically, it requires you to have precise, preloaded data about the known pulsars, their positions, their timing parameters, their slowdown rates. That data has to be measured and stored before you leave. It's like having a detailed map of the city you're visiting, incredibly useful, right up until you wander somewhere the map makers never charted, in truly deep space, in intergalactic voids, in regions far from any catalogued pulsar. That preloaded map runs out, and beyond its edges there is nothing. No GPS, no lighthouse, no signal of any kind telling you where you stand in the cosmos. Now I want to bring in something that sits beneath all of these practical challenges, something that operates at the level of physics itself, not technology, not data, not engineering. Something that would pose a problem even to a civilization 1,000,000 years more advanced than ours. It's called the relativity of simultaneity, and it comes from Albert Einstein's special theory of relativity, first published in 1905 a year that changed physics forever and quietly rearranged everything humanity thought it understood about space and time. Here's the core of it, stated as plainly as I can manage. In our everyday experience, time feels universal. You and I might be in different cities, different countries, different time zones, but we share the same now, the same present moment. If I snap my fingers at exactly noon and you're in a city 10,000 kilometers away, it feels intuitively obvious that we both experience that snap as happening at noon, even if we're far apart. Time, it seems, flows at the same rate everywhere, and events happen at the same when for everyone. Einstein showed that this intuition is wrong, profoundly, irreversibly, experimentally confirmed wrong. The rate at which time flows depends on two things: how fast you're moving and how deep you are in a gravitational field. Move faster, and time moves more slowly for you relative to someone who is stationary. Sit deeper in a gravitational well, closer to a massive object, and time ticks more slowly for you relative to someone in weaker gravity. These effects are not large in everyday life, but they are real, they are measurable, and they accumulate over cosmic distances and timescales into differences that cannot be ignored. For deep space navigation, this creates a problem that has no clean solution. If a spacecraft has been traveling at a significant fraction of the speed of light, which any practical interstellar mission would need to do, time aboard that ship has been passing at a different rate than time back on Earth. When the crew tries to use stellar positions, pulsar timings, or any other time-dependent navigation method, they have to account for this difference. The universe they're looking at has aged differently than the universe they left behind. Their clocks and the cosmos's clocks are no longer synchronized, and the maths required to reconcile those differences, while theoretically understood, would have to be applied to every single measurement, introducing layers of uncertainty that stack on top of each other with every passing light year. This is not science fiction. These effects are real, and we account for them right here on Earth. The GPS satellites orbiting our planet are moving at speeds high enough and operating in gravitational conditions different enough from the surface that their onboard clocks run at a slightly different rate than clocks on the ground. If those corrections weren't applied continuously, adjustments based directly on Einstein's equations, the GPS system would drift by roughly 11 kilometers per day. We already live in a world where relativistic time correction is a practical engineering requirement. Extend that into deep space, and the corrections don't just get larger. They become interwoven with every other navigational uncertainty in ways that are genuinely difficult to untangle, and somewhere in that tangle, between the ancient light, the expanding universe, the slowing pulsars, the curved space-time, and the relativistic clocks, lies the answer to why finding your way home in deep space is not just hard. It is, in a very real and beautiful and humbling sense, a problem that cuts right to the core of what the universe is and how it works. Now we explore somewhere even stranger into the structure of the Milky Way itself, and why our galaxy's own architecture makes getting lost an almost inevitable outcome. Don't go anywhere. Let's talk about where we live. Not your city, not your country, not even your planet. Let's zoom all the way out and talk about the structure of the place we call home at the largest scale we can still reasonably call a neighborhood: the Milky Way galaxy. Because before we can fully appreciate what it means to be lost in deep space, we need to understand just how disorienting the place we came from actually is, even from the inside. Here is something that might genuinely surprise you. Despite living inside the Milky Way, despite it being, in the most literal sense, the galaxy that made us, we have never seen it from the outside. Not once. Every image you've ever seen of a beautiful sweeping spiral galaxy, arms curling gracefully outward from a glowing central bulge, Stars and dust and gas woven together into something that looks almost deliberately beautiful. Every one of those images is a picture of a different galaxy, not ours. We have never had the vantage point to photograph our own home from the outside, and we won't for a very long time, if ever. We are inside it, we are part of it, and mapping something from the inside, when you can't step back and look at the whole picture, is one of the oldest and most stubborn problems in astronomy. Think of it this way. Imagine you're standing in the middle of a dense forest, trees in every direction as far as you can see. You want to draw a map of the forest, its shape, its boundaries, the way the trees cluster in some areas and thin out in others. But you can only see a few hundred meters in any direction before the view becomes obscured. You can look up and see patches of sky, and from the angle of the sun you can work out roughly which direction is north. But the full shape of the forest, its extent, its outline from above, is completely invisible to you. You have to infer it. You have to measure distances to individual trees, note what species they are, estimate how densely they're packed, and then build up a picture of the whole from thousands of individual data points, knowing all the while that some of those data points might be misleading. That is almost exactly the situation astronomers have faced in mapping the Milky Way. And the map they've built, painstakingly, over many decades, using radio telescopes, infrared observatories, and most recently the extraordinary Gaia Space Telescope, is still incomplete, still uncertain in important ways, and in some regions still actively being revised. Here's what we know. The Milky Way is a barred spiral galaxy. That barred part is important. It means that instead of spiral arms emerging directly from a central point, they emerge from the ends of an elongated bar of stars that runs through the center of the galaxy. This bar is roughly 27,000 light-years long. The overall disk of the Milky Way stretches somewhere between 100,000 and 160,000 light-years across, depending on how you define its outer edge, and that uncertainty in the size of our own galaxy tells you something about how hard this mapping problem really is. Our solar system sits roughly 26,000 light-years from the galactic center, about halfway out, positioned between two of the major spiral arms, in a smaller structure called the Orion Arm, or sometimes the Orion Spur. We orbit the center of the galaxy at a speed of approximately 220 kilometers per second. Even at that incredible speed, one full orbit, one galactic year, takes approximately 225 million Earth years. The last time our solar system was in its current position in the galaxy, the dominant life forms on Earth were early dinosaurs. We have completed fewer than 21 full orbits since the solar system formed 4.5 billion years ago. Now, let's say you're a hypothetical spacecraft that has traveled far enough from the Milky Way to lose your bearings. Maybe you've gone intergalactic. Maybe you've drifted into one of the vast cosmic voids. Regions of space, hundreds of millions of light-years across where galaxies are essentially absent, where the density of matter drops to almost nothing, and you're trying to find your way back. You look for the Milky Way, you search the sky for that familiar spiral pattern. And here is the first problem that hits you immediately, even before all the ones we've already discussed. You don't know what the Milky Way looks like from the outside. Not precisely, not in enough detail to recognize it with confidence from an arbitrary vantage point in intergalactic space. We have models. We have simulations built from decades of observation and increasingly powerful computational tools. The Gaia Space Telescope, a European Space Agency mission that has been operating since 2013 and has mapped the positions and motions of nearly 2 billion stars within the Milky Way with extraordinary precision, has given us our best ever picture of the galaxy's structure. But Gaia maps the galaxy from the inside. Its data is a three-dimensional census of stars in our cosmic neighborhood, not a photograph from the outside. Translating that internal map into a precise prediction of what the Milky Way would look like from, say, 5 million light-years away, from a specific angle at this particular moment in cosmic time, that is an inference. A very educated inference built on solid physics, but an inference nonetheless. And here's the thing about inferences in deep space. The margin of error is not small. A slight uncertainty in the estimated shape of one spiral arm translates into a navigational uncertainty of thousands of light years, which, if your goal is to return to a specific star in a specific arm, a star we call the Sun, might as well be a different galaxy entirely. Let's bring in something that makes this even more concrete. In 2019, a team of astronomers published a remarkable study using data from the Gaia telescope combined with observations from other surveys. What they found was that the disk of the Milky Way is not flat, it is warped, bent. Like a vinyl record left too long in the sun, the outer regions of our galaxy's disk curl upward on one side and downward on the other in a shape astronomers describe as a warp. And not only is it warped, the warp is rotating, precessing in the technical language. The bent edge of our galaxy is slowly turning, completing a rotation of the warp over a timescale of roughly 640 million years. This was not entirely unexpected. Warped galaxies are actually quite common, and the physical mechanisms that cause them, including gravitational interactions with satellite galaxies like the Large and Small Magellanic Clouds, are reasonably well understood. But the precision with which Gaia allowed scientists to measure and characterize this warp was genuinely new. And what it tells us from a navigational standpoint is that the Milky Way is not a static, predictable object. It is dynamic, it is changing. Its shape today is not its shape from 100 million years ago, and it will not be its shape 100 million years from now. For a traveler trying to navigate by the shape of our galaxy across truly long timescales, this matters. The map is not just hard to read from the outside, it is slowly changing while you're trying to read it. And then there are the satellite galaxies. The Milky Way is not alone. It is accompanied by a collection of smaller companion galaxies bound to it gravitationally, orbiting around it in a complex and not entirely predictable fashion. The most prominent of these are the Large and Small Magellanic Clouds, irregular dwarf galaxies visible to the naked eye from the southern hemisphere, sitting at distances of roughly 160,000 and 200,000 light-years respectively. There are also dozens of smaller satellite galaxies, some of them discovered only in recent years thanks to deep sky surveys sensitive enough to pick up the extremely faint stellar populations of ultra-diffuse dwarf galaxies. These companions add clutter to the picture. If you're approaching the Milky Way from intergalactic space, trying to identify your home galaxy from among the crowd, the surrounding swarm of satellite galaxies doesn't make the task easier. It adds ambiguity. Which smudge of light is the main galaxy, and which are the companions? From certain angles at certain distances, the answer might not be immediately obvious. Now add one more layer. The Milky Way is itself part of a larger structure. Our galaxy and the Andromeda Galaxy, along with dozens of smaller companions, form what astronomers call the local group, a gravitationally bound collection of galaxies roughly 10 million light-years across. Beyond the local group, on still larger scales, we belong to the Virgo supercluster, a vast, loosely connected assembly of galaxy groups and clusters, stretching roughly 110 million light-years across. And even the Virgo supercluster is just one tendril of an even larger structure called Laniakea, a cosmic superstructure roughly 520 million light-years across, containing the mass of approximately 100 million billion suns, first mapped by a team led by astronomer Brent Tully in 2014 using galaxy velocity data. Each of these structures is nested inside the next, like cosmic Russian dolls, and while knowing about them gives us a richer, more complete picture of our place in the universe, from a navigational standpoint they add complexity rather than clarity, because each scale of structure comes with its own gravitational dynamics, its own patterns of motion, its own history of formation and evolution. To navigate using these structures as landmarks, you would need to know their current positions and configurations with a precision that our observations simply don't yet provide. Here's something I find genuinely beautiful about all of this. Even in the middle of what is essentially a catalogue of navigational impossibilities, the fact that we know about the warp of the Milky Way, the fact that we have mapped Laniakea, the fact that we can describe the orbital period of our solar system around the galactic center to within a few million years, or identify the precise distance to the galactic bar using radio observations of hydrogen gas clouds. These are not small achievements. They represent centuries of accumulated human curiosity, translated into instruments, translated into data, translated into understanding. Every one of those measurements was made by someone who looked up and refused to accept ignorance as an answer. And yet, and this is the tension that I think makes this topic so rich, knowing all of that still doesn't solve the navigation problem. It illuminates it. It defines its edges with greater precision. It tells us with beautiful clarity exactly how hard the challenge is, but it does not dissolve it. This is, I would argue, one of the most honest things science can do. Not to pretend that knowledge eliminates mystery, but to use knowledge to understand mystery more deeply, to stand at the edge of what we know and describe with rigor and humility the shape of the darkness beyond. Now, I want to talk about something that has been lurking in the background of everything we've discussed so far. Something that exists not in our technology, not in our measuring instruments, not even in the structure of the galaxy, but in the fabric of space-time itself. Something that would complicate deep space navigation even if you had perfect instruments and perfect data and unlimited time. Dark matter, and its even stranger companion, dark energy. These are not fringe ideas. They are not speculative hypotheses confined to the margins of physics. They are the dominant components of the universe, and they are, by definition, invisible, undetectable by any instrument that relies on electromagnetic radiation, which is to say, any telescope ever built of any kind, looking at any wavelength. We know they exist because of what they do to the things we can see, but we cannot see them directly. And in a universe where navigation depends on knowing what's out there, on having a complete and accurate map of the forces and structures that will pull on your spacecraft as it moves, the existence of two massive, invisible components of reality is not a minor inconvenience. It is a fundamental problem. Let me give you the numbers, because the numbers here are genuinely staggering. According to our best current models of cosmology, models built on decades of observation from missions like Planck, the Hubble Space Telescope, and the Dark Energy Survey, ordinary matter, the stuff made of protons and neutrons and electrons, the stuff that makes up every star, every planet, every human being, every atom of every molecule of everything you have ever touched or seen or thought about, that ordinary matter accounts for approximately 5% of the total energy content of the universe. 5%. The remaining 95% is divided between dark matter, approximately 27%, and dark energy, approximately 68%. And we do not know what either of them fundamentally is. We know dark matter exists because of the way galaxies rotate. Stars in the outer regions of spiral galaxies orbit the galactic center faster than they should, given the amount of visible matter present. The only explanation consistent with our understanding of gravity is that there is additional invisible mass distributed throughout and around the galaxy, providing the extra gravitational pull needed to explain the observed orbital speeds. This invisible mass is dark matter. Its gravitational effects are real, measurable, and thoroughly documented. The Bullet Cluster, a pair of galaxy clusters that collided and passed through each other roughly 150 million years ago, provided one of the most compelling pieces of evidence for dark matter's existence when observations showed that most of the mass of the system had passed through the collision without interacting, while the hot gas clouds had been slowed and separated. The mass that passed through without interacting, dark matter, but despite knowing it's there, despite having mapped its distribution in broad strokes using gravitational lensing, the way massive objects bend light passing near them, allowing us to infer the location of mass we can't see directly, we have never directly detected a dark matter particle. Every purpose-built detector, buried deep underground to shield it from cosmic ray interference, has so far come up empty. The nature of dark matter remains one of the deepest open questions in physics. For a navigator, dark matter matters. Forgive the repetition, because it is one of the dominant sources of gravitational influence on the large-scale structure of the universe. The cosmic web, the vast network of filaments and sheets and voids that defines the large-scale geography of the cosmos, was shaped by dark matter. Galaxies formed where dark matter concentrations created the gravitational seeds for ordinary matter to collapse into stars and structures. To navigate the large-scale universe accurately, you would need to account for the gravitational influence of dark matter. And to do that, you would need to know its distribution with a precision we currently don't have. Dark energy is a different kind of mystery. It doesn't clump or cluster. It doesn't form structures. It is distributed uniformly throughout space, in every corner of the universe, at every location, and its effect is not to attract but to push. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. Not just continue, accelerate. The expansion is speeding up. Galaxies are not just moving apart. They are moving apart faster and faster over time, driven by this mysterious energy embedded in the fabric of space itself. This was discovered in 1998, simultaneously by two independent research teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rias, using observations of Type Ia supernovae as standard candles to measure distances across cosmic scales. The result was so unexpected, so at odds with what almost everyone had assumed, that it took the scientific community years to fully accept it. Eventually it did. Perlmutter, Schmidt, and Rias were awarded the Nobel Prize in Physics in 2011 for this discovery. The accelerating expansion means something profound for deep space navigation. It means that the universe has a horizon, not in the way the Earth has a horizon, but in a deeper, more final sense. Objects beyond a certain distance are already receding from us faster than light can travel. Not because they're moving through space faster than light, that would violate relativity, but because the space between us and them is expanding so quickly that light trying to cross that gap never quite makes it. Those objects are, in a very real physical sense, permanently beyond our reach. We can never visit them. We can never receive new information from them. They are gone from our universe not because they've been destroyed, but because the expanding fabric of space-time has carried them over an unreachable horizon. That horizon, called the cosmological event horizon, sits at a distance of roughly 16 billion light-years from us today. Beyond it, the universe continues, but it continues in silence as far as we will ever be concerned. And that horizon is shrinking. Every moment more of the universe passes beyond it, driven by the accelerating expansion, lost to us forever. For a navigator in deep space, this has an almost poetic cruelty to it. The universe isn't just hard to navigate, it is actively removing its own landmarks. Every year, more galaxies cross the event horizon and disappear from the reachable universe. The map is not just incomplete, it is shrinking. The territory available to us is getting smaller, not larger. Even as our telescopes get more powerful and our understanding deepens, we are, in a sense, navigating a universe that is in the process of erasing itself. And yet, and I mean this sincerely, I find that beautiful, because it means that right now, at this precise moment in cosmic history, we have access to a universe that is richer in visible structure, in reachable destinations, in observable landmarks than it will ever be again. The universe we live in today, with its hundreds of billions of galaxies still within the observable horizon, is the most navigable version of the universe that any future civilization will ever inherit. We are here at what might be, in some sense, the golden age of cosmic exploration. That thought should not make you feel small. It should make you feel extraordinarily, improbably lucky. We will get into something even more immediate. The actual mechanics of how spacecraft navigate right now, what the real limits of our current systems are, and what the most creative minds in aerospace engineering are proposing to push past those limits. You will not want to miss this one. So far, we've been living in the theoretical. We've talked about the nature of light, the expansion of the universe, the invisible architecture of dark matter, the warped disk of our own galaxy. All of it real, all of it verified by observation and experiment, and all of it profoundly humbling. But now I want to bring this conversation back to something more immediate, more human, more mechanical, because right now, today, in the year we are living in, humanity has spacecraft out there, real machines built by real engineers, launched by real rockets, traveling through real space. And those spacecraft have to navigate. They have to know where they are and where they're going, and the methods we use to keep track of them, methods that represent the absolute cutting edge of human navigational capability, reveal, perhaps more clearly than anything else we've discussed, exactly where our abilities end and the true scale of the problem begins. Let's start with how we actually navigate spacecraft right now. Because the answer is, in some ways, surprisingly old-fashioned, and in other ways, it is a genuine triumph of human ingenuity operating right at the boundary of what physics allows. The primary method used to navigate deep space probes today is called radiometric tracking. In plain language, this means we send a radio signal from Earth to the spacecraft, and the spacecraft sends one back. By measuring the time it takes for the signal to make the round trip, and by analyzing the precise frequency of the returned signal, looking for the Doppler shift caused by the spacecraft's motion toward or away from us. Engineers on the ground can calculate both the distance to the spacecraft and its velocity along the line of sight from Earth. Do this from multiple ground stations at different locations on Earth's surface, and you can build up a three-dimensional picture of the spacecraft's position and trajectory. This is the system used by NASA's Deep Space Network, the same network of enormous dish antennas we mentioned in Part 1, and it works with extraordinary precision. For a spacecraft like the New Horizons probe, which flew past Pluto in July of 2015, returning the first close-up images of that distant world and revealing it to be a geologically active, strikingly beautiful place with nitrogen ice plains and mountain ranges of water ice rising 3.5 kilometers above the surface. The navigation team was able to predict the spacecraft's position at closest approach to within a handful of kilometers after a journey of nearly 5 billion kilometers. That is a level of precision equivalent to shooting a bullet from one city and hitting a specific centimeter-sized target in another city on the other side of the planet. It is, without exaggeration, one of the most impressive feats of applied mathematics in human history. But, and here is the crucial limitation, this method requires Earth. It requires the ability to send signals back and forth between the spacecraft and our antennas on the ground. It requires that the spacecraft remain in contact with home. The moment that contact is broken, whether through distance, interference, or any other cause, the method stops working, and at the distances of true deep space, even maintaining that contact becomes a monumental challenge. Consider the signal strength problem. Radio signals obey what physicists call the inverse square law. Their intensity decreases with the square of the distance. Double the distance, and the signal is 4 times weaker. Triple the distance, and it is 9 times weaker. At the distance of Voyager 1, more than 23 billion kilometers from Earth, the signal received by our largest antennas is extraordinarily faint. We're talking about a power level of roughly 10 to the power of negative 16 watts. That is a decimal point followed by 15 zeros and then a 1. The transmitter on Voyager itself puts out just 22 watts, roughly the same as a dim light bulb. By the time that signal crosses the void and arrives at Earth, it has been diluted by distance into something almost unimaginably tenuous. Only the largest antennas on the deep space network, with their 70-meter dish diameters, can reliably receive it. Now extend that distance by orders of magnitude to the nearest star, to the center of the galaxy, to the Andromeda galaxy. At those distances, the inverse square law doesn't just make the signal weaker, it makes it functionally non-existent. No antenna of any physically plausible size could receive a signal transmitted at those ranges with current technology. The radiometric tracking method, brilliant and precise as it is, has a hard ceiling set by the laws of physics, and that ceiling is nowhere near high enough for true deep space navigation. So what are the alternatives? What are the most creative and rigorous proposals on the table right now for navigating beyond the reach of Earth's radio signals? There are several, and they are genuinely fascinating. Let's go through them one by one, because each one reveals something important about both the ingenuity of the people working on this problem and the stubborn nature of the obstacles they're facing. The first is the pulsar navigation system we touched on in part 2, but let's go deeper into the practicalities now. The NICER experiment on the International Space Station demonstrated position determination to within roughly 5 kilometers using X-ray pulsar timing. That sounds impressive, and it is, but consider the context. 5 kilometers of uncertainty might be acceptable if your destination is a large region of space. It is completely unacceptable if you're trying to rendezvous with a specific object, dock with a specific station, or land on a specific world. For comparison, when the Perseverance rover landed on Mars in February of 2021, it touched down within approximately 1 kilometer of its target landing site, and that was considered a remarkable achievement of precision navigation, made possible by years of careful trajectory planning and real-time Earth-based tracking. Pulsar navigation, in its current form, could not achieve that level of precision independently. There are also engineering challenges involved in implementing X-ray pulsar navigation on a deep space probe. X-ray detectors require shielding from background radiation. They have mass and power requirements. The onboard processing needed to measure pulse arrival times with nanosecond precision is computationally demanding. None of these are insurmountable obstacles. They are engineering problems, and engineering problems get solved. But they add mass and complexity to spacecraft that are already tightly constrained by the physics and economics of rocket launch. Every kilogram of detector hardware is a kilogram that can't be fuel, or science instruments, or structural support. The second approach is autonomous optical navigation, using onboard cameras to observe the positions of stars and other celestial bodies, and comparing those observations to a preloaded star catalogue to determine position. This is actually not a new idea. Humans have been navigating by the stars for as long as we've been capable of looking up at them. The ancient Polynesian navigators who crossed the Pacific Ocean in outrigger canoes used stellar positions, ocean swells, and bird behavior to cross thousands of kilometers of open water with extraordinary accuracy. Celestial navigation was the backbone of maritime exploration for centuries, and the principle translates, with some modifications, to spacecraft. The New Horizons spacecraft, among others, used onboard optical navigation, photographing target bodies against the background star field and using the measured positions to refine the trajectory estimate. The Hayabusa 2 mission, a Japanese aerospace exploration agency spacecraft that collected samples from the asteroid Ryugu and returned them to Earth, used a combination of ground-based radiometric tracking and onboard optical navigation to achieve the extraordinary precision needed to land on a small, irregularly shaped asteroid and collect material from its surface. But optical navigation in deep space runs into fundamental limits too. Stars are the reference points, and stars, as we've discussed, have proper motions. They move relative to each other, slowly but continuously, driven by their individual orbits around the galactic center, over the timescales relevant to truly long-distance interstellar travel, thousands or millions of years. The star patterns you loaded into your catalog before departure would gradually drift away from the patterns you actually observe. The constellation shapes we see in our night sky tonight are not the same ones our ancestors saw 100,000 years ago, and they will not be the ones any future civilization observes 100,000 years from now. The sky is not fixed. It is a slowly shifting mosaic of moving lights, and its patterns are only stable on human timescales. Beyond the Milky Way entirely, in intergalactic space, the star field thins to near zero. There are no nearby stars to use as reference points. The galaxies you can observe are so distant that their angular positions change immeasurably slowly, too slowly to use for precise triangulation. You are navigating in a space that offers almost no handholds. The third approach, and arguably the most futuristic, is inertial navigation, keeping track of every acceleration the spacecraft has ever experienced since leaving a known starting point, and using that accumulated record to calculate current position through dead reckoning. This is essentially what submarines use when they're running silent beneath the ocean, unable to access GPS signals. Highly sensitive accelerometers measure every change in velocity, and a computer integrates those measurements over time to maintain an estimate of position relative to the starting point. The problem with inertial navigation over very long distances is that errors accumulate. No accelerometer is perfectly accurate. Every measurement has a tiny uncertainty. And when you integrate those uncertainties over months, years, or decades of travel, the errors grow. They don't grow linearly. They grow in a way that depends on the type and quality of the sensors, but they always grow. A submarine using inertial navigation needs to periodically come up and check its position against an external reference, a GPS fix, a known landmark, a radio signal to reset the accumulated error. In deep space, with no external references available, there's no way to perform that reset. The error just keeps building. Over interstellar distances, the uncertainty in position calculated purely by inertial navigation would be enormous. There is a proposed solution to this that involves quantum technology, and it is one of the most exciting frontiers in navigation science right now. Quantum accelerometers, devices that use the quantum mechanical behavior of ultracold atoms to measure acceleration with extraordinary precision, offer the potential to reduce the error accumulation rate dramatically compared to conventional sensors. Research into atom interferometry, a technique that exploits the wave-like nature of atoms to make extremely sensitive measurements of acceleration and rotation, is ongoing at laboratories around the world. including groups funded by space agencies actively interested in its navigation applications. In 2020, a team of researchers demonstrated atom interferometry in a microgravity environment for the first time aboard a sounding rocket that briefly achieved weightlessness during its parabolic flight. The results were published in the journal Nature and represented a significant milestone in the practical development of quantum inertial sensors. The precision achieved was not yet at the level needed for interstellar navigation, but the trajectory of improvement, if you'll forgive the navigational pun, is encouraging. But even with perfect quantum sensors, there remains a conceptual problem with pure inertial navigation that no amount of engineering finesse can resolve. And that problem goes back to something Einstein identified more than a century ago. In general relativity, the curvature of spacetime affects the paths that objects travel along, including spacecraft. A probe moving through a region of space near a massive object, or through a region where the spacetime curvature is significant for any reason, will follow a curved path even if no engine is firing. From the probe's own perspective, it is traveling in a straight line, but a straight line in curved spacetime is not the same as a straight line in flat space. The probe's inertial sensors won't register this curvature as an acceleration because, in general relativity, free fall through curved spacetime is indistinguishable from inertial motion. You can't feel gravity in free fall. Einstein called this the equivalence principle, and it is one of the deepest insights in the history of physics. The practical consequence is that a spacecraft relying purely on inertial navigation cannot distinguish between "I am traveling in a straight line through flat space" and "I am traveling along a curved path through curved space." To account for space-time curvature, you need an independent measurement of the gravitational environment, which requires either external reference points or an extraordinarily detailed model of the mass distribution throughout the entire region of space you're traveling through. And we don't have that model and won't for the foreseeable future. Dark matter alone sees to that. I want to pause here and bring in a real mission that illustrates just how razor-thin our navigational margin already is, even within our own solar system, because I think it makes everything we've been discussing feel less abstract. In January of 2019, NASA's New Horizons spacecraft, already more than 6.5 billion kilometers from Earth, nearly 1 billion kilometers past Pluto, performed a flyby of a small Kuiper Belt object designated 2014 MU69, later named Arrokoth. It was the most distant flyby of any object in history. Arrokoth turned out to be a contact binary, two lobes gently pressed together like a cosmic snowman, formed when two separate bodies drifting through the Kuiper Belt gradually spiraled together under their mutual gravity billions of years ago. Its reddish color, its pristine surface, its gently flattened shape, all of it spoke to a history stretching back to the very dawn of the solar system, preserved in the cold dark beyond the planets like a message in a bottle from 4.5 billion years ago. The navigation required to hit that flyby was breathtaking. Arrokoth is only roughly 36 kilometers in its longest dimension. New Horizons had to thread a gap defined not in millions of kilometers, but in thousands, passing within approximately 3,500 kilometers of a target that was itself moving through space, while the spacecraft was also moving, while the entire solar system was also moving, while all of this had to be computed from a distance of over 6 billion kilometers with a communication delay of more than 6 hours one way. And they did it. The flyby was successful, the images came back, the data told a story, and the people who made it happen did so using Newtonian mechanics, general relativistic corrections, careful starfield measurements, and the deep space network. But here's the thing I want you to notice. That mission one of the most ambitious navigational achievements in human history, still relied entirely on Earth, on the deep space network, on the continuous thread of radio signals connecting New Horizons to the people tracking it from the ground. Cut that thread, and the mission would have no way to know where it was going. It would continue on its trajectory, governed by the physics of its last known state, with no ability to correct, to adjust, to respond to unexpected gravitational influences, or to confirm its own position. That thread, that fragile, 22-watt thread of radio waves crossing 6 billion kilometers of void, is the lifeline that connects all of our deep space missions to the navigational knowledge they need to function. It is a stunning achievement, and it is nowhere near enough for what comes next. Here's the question that I think deserves to be asked out loud, because it's the one that sits underneath everything we've been building toward. If we ever develop the capability to send humans, or even robotic probes to another star, how would they navigate? Not just to get there, but to get back. How do you maintain a sense of where home is across 4, 10, 50, 100 light years of space? Across a journey that might last decades or centuries, during which Earth continues to orbit the Sun continues to orbit the galactic center, and the entire Milky Way continues its slow gravitational dance with its neighbors. There is no fully satisfying answer to that question yet. There are proposals, there are ideas being developed with genuine rigor, but none of them, as of now, constitutes a complete solution. The pulsar network helps but has limits, optical navigation helps but has limits, quantum inertial sensors help but have limits. Combining all of them, creating a layered, redundant navigation system that draws on every available source of information is almost certainly the direction any serious interstellar mission would need to go. But the gaps between what that system can provide and what a crew would actually need across the distances and timescales involved remain significant, and underneath all the technology, underneath all the engineering, there is still the fundamental physics, the expanding universe, the curvature of space-time, the finite speed of light, the invisible architecture of dark matter. These are not engineering problems. They cannot be solved by building a better antenna or writing a smarter algorithm. They are properties of the universe itself, baked into the structure of reality at the deepest level, which brings us to something I find both deeply sobering and quietly magnificent. The universe does not appear to have been designed with navigation in mind. It does not offer fixed landmarks, stable reference frames, or instant communication. It offers distance and time and uncertainty and expansion. It offers a cosmos that is vast beyond all meaningful comprehension, governed by physics that makes finding your way an act of almost philosophical defiance. And yet, here we are, defying it anyway, sending our machines into the void, threading needles across billions of kilometers, listening to the faint whispers of spinning neutron stars, mapping the invisible web of dark matter through its gravitational shadow, measuring the rate at which the universe is flying apart, and arguing about whether our two best methods for doing so actually agree. We are a species that looks at an impossible problem and builds a rover, that looks at an unreachable world and finds a way to take its temperature, that sits in the warm gravity of a small planet orbiting an ordinary star in the unfashionable outer arm of a mid-sized galaxy, and somehow works out the large-scale structure of the universe it lives inside. That is not nothing. That is, I would argue, one of the most remarkable things that has ever happened in 13.8 billion years of cosmic history. If you are enjoying this journey, make sure to subscribe to the channel. You will be part of a community that explores the cosmos together. Now let's go somewhere even more extraordinary. This one is going to reshape the way you think about space. Stay with me. I want you to try something. Hold your hand out in front of you, flat, palm facing down. Now point one finger straight ahead. That finger is pointing in a direction, a clear, unambiguous, geometrically precise direction, forward. And if you kept walking in that direction, if you never turned, never curved, never deviated, your intuition tells you that you would keep going forward forever, straight, infinite, never returning to where you started. That intuition is correct on the surface of a flat piece of paper. It is correct in the abstract mathematical space your geometry teacher described in school, but it may not be correct in the actual physical universe you live in, because the universe is not a flat piece of paper, and the geometry that governs it, the real geometry, the one Einstein described and observations have since confirmed, is something altogether stranger and more interesting than the flat, infinite grid most of us instinctively picture when we close our eyes and imagine space. This is where we need to talk about the shape of the universe. And I want to be upfront with you right from the start. This is one of those topics where the honest answer is that we genuinely do not know the full truth yet. We have measurements, we have constraints, we have strong theoretical preferences, but the definitive answer, the final, confirmed shape of the universe at its largest scales, remains one of the open questions at the frontier of cosmology. And I think that uncertainty is not a weakness of science. It is science doing exactly what it's supposed to do, telling you the truth about what it knows, and being honest about what it doesn't so. What do we mean by the shape of the universe, and why does it matter for navigation? In general relativity, gravity is not a force in the traditional sense. It is a curvature. Massive objects, stars, planets, black holes, galaxy clusters bend the fabric of space-time around them, and other objects moving through that space-time follow the curves. This is why the Earth orbits the Sun, not because the Sun is pulling the Earth across flat space with some invisible rope, but because the Sun's mass curves the space-time around it, and the Earth, moving through that curved space-time, follows a path that brings it back around again and again. A straight line in curved space-time is called a geodesic, and geodesics can be curves in the ordinary sense, even closed loops, depending on how the space-time is shaped. Now, this curvature happens locally around specific massive objects. But general relativity also allows for the possibility of global curvature, a curvature of space-time not caused by any particular object, but built into the large-scale geometry of the universe as a whole. And that global curvature, if it exists, would have profound consequences for navigation. There are three basic possibilities, and cosmologists have a beautifully simple way of describing them. The first possibility is a flat universe. In a flat universe, the geometry of space on the very largest scales obeys the Euclidean rules you learned in school. Parallel lines never meet. The angles of a triangle add up to exactly 180 degrees. A straight line extending forever in one direction never returns to its starting point. The universe just goes on, infinite in every direction with no overall curvature to its geometry. The second possibility is a positively curved universe, sometimes called a closed universe, where the geometry of space is analogous to the surface of a sphere. On a sphere, parallel lines eventually meet. The angles of a triangle add up to more than 180 degrees, and crucially, if you travel in a perfectly straight line for long enough, you eventually come back to where you started. A closed universe is finite but has no boundary. There is no edge, no wall, no place where space ends. You just loop back around, like an ant walking along the surface of a very large ball. The third possibility is a negatively curved universe, sometimes called an open universe, where the geometry is analogous to the surface of a saddle. In a saddle-shaped geometry, parallel lines diverge away from each other. The angles of a triangle add up to less than 180 degrees. Straight lines never return. Now, which one is our universe? This is where the measurements come in, and the answer, according to our best current data, is flat, or at least extraordinarily close to flat. The Planck satellite's precise measurements of the cosmic microwave background, that ancient light from the early universe that carries imprinted within it the fingerprints of the geometry of space, give a value for what cosmologists call the density parameter, designated by the Greek letter omega of 1.001 plus or minus 0.002. A perfectly flat universe has an omega of exactly 1. Our measured value is indistinguishable from one within the current margin of error. The universe, as best we can measure it, is flat, but here is the navigational twist, and it is a genuinely strange one. Flat does not necessarily mean infinite, and this is where topology enters the picture, a branch of mathematics that deals not just with geometry, but with the overall connectedness and structure of a space. Two surfaces can have identical local geometry, identical curvature at every point, while having completely different global structures. Think of a flat piece of paper versus a cylinder. Both are locally flat. At any given point on either surface, the geometry obeys Euclidean rules, but a cylinder, unlike a flat sheet, is connected to itself in one direction. If you travel along a cylinder in the direction of its circumference, you come back around, and you could, in principle, build a surface that is locally flat but connected to itself in two directions, like a donut or torus in the mathematical sense, locally flat everywhere, globally looping back on itself. The universe could be like that, locally flat, consistent with everything Planck measured, but globally connected in ways that would cause a straight-line journey in one direction to eventually bring you back around to where you started. This is called a multiply-connected topology, and it has been seriously proposed and seriously studied. If the universe has a compact topology, if it loops back on itself at some scale, then there would be a characteristic scale at which this looping occurs. And if that scale is smaller than the observable universe, we might be able to detect it. How? By looking for repeated patterns in the cosmic microwave background. If light from the early universe has had time to travel around the universe and come back to us from the opposite direction, certain patterns in the CMB should appear in multiple places in the sky, a kind of cosmic echo that would tell us the universe is smaller than it appears, and that the same regions of space are visible from multiple angles. The Planck team looked for exactly these signatures, and the answer, at least for the scales they were able to probe, is that no convincing evidence of a compact topology has been found. If the universe loops back on itself, it does so at a scale larger than our current observational horizon. The loop, if it exists, is bigger than the bubble of universe we can see, which means we can't rule it out. We simply can't see far enough to know. And for navigation, for a spacecraft that might hypothetically travel far enough and long enough, this matters. Because in a universe with a compact topology, a straight-line journey in one direction might eventually be a journey home. You wouldn't need a map, you would just need to keep going. The universe's own geometry would eventually bring you back around. But eventually, in this context, might mean traveling for a distance larger than the entire observable universe. A journey measured not in light years or even millions of light years, but in the tens of billions. A journey so long that the ship, the civilization that built it, and the star it was trying to return to would all be gone before the geometry delivered its promise. Let's come back to something more immediate, but no less strange, the curvature of space-time around massive objects, the local geometry as opposed to the global topology, and what it does to the paths that light and matter travel along. One of the most visually striking predictions of general relativity is gravitational lensing. When light from a distant object passes near a massive foreground object, a galaxy cluster, a black hole, the curved space-time around that massive object bends the light's path. The result, seen from Earth, is that the background object appears distorted. Sometimes it appears as an arc, sometimes as multiple images of the same object arranged symmetrically around the lensing mass. And sometimes, when the alignment between the background source, the lensing object, and the observer is nearly perfect, the background object appears as a complete ring of light, a circle of brightness surrounding the lensing mass, called an Einstein ring, first predicted by Einstein himself and subsequently observed in multiple systems. Gravitational lensing is not just a visual curiosity. It is a practical phenomenon with real consequences for anyone trying to navigate in deep space. Light does not travel in straight lines near massive objects. It follows geodesics, the straightest possible paths through curved space-time, and those geodesics are curves in the conventional sense. Which means that if you try to navigate by the apparent position of a star or galaxy, and your line of sight passes near a massive object, the position you observe is not the true position. The light has been bent. You are seeing the source as if it were somewhere it isn't. For missions within our solar system, this effect is measurable but manageable. We know where the massive objects in our neighborhood are. We can calculate the expected deflection, and we can correct for it. But in deep space, surrounded by unknown distributions of mass, including the dark matter we cannot directly observe, the lensing corrections become much harder to calculate. The bending of light by dark matter halos, galaxy clusters, and other massive structures scattered throughout the cosmos introduces positional uncertainties that compound with distance. Every measurement of a distant object's position carries with it an uncertainty associated with whatever mass might lie along the line of sight. Mass we may not be able to account for because we cannot see it. There is an even more extreme version of this phenomenon that deserves a moment of attention because it perfectly encapsulates the way that the universe's own architecture resists navigation. Near a black hole, a region of space-time where the curvature becomes so extreme that not even light can escape past a certain threshold called the event horizon. The bending of light is not just significant, it is total. Light paths curve so severely that photons can orbit the black hole. There is a region around every black hole called the photon sphere where light travels in circles. Imagine that for a moment. Light, the fastest thing in the universe, the thing that travels in straight lines through flat space, the thing we use to see everything, moving in closed circles around a gravitational singularity. In that environment, the very notion of using light to navigate breaks down completely. The directions from which light reaches you no longer correspond in any simple way to the directions of the objects that emitted it. The geometry of space-time around a black hole is so severely distorted that your intuitive sense of where things are becomes meaningless. You would need to solve Einstein's field equations in their full complexity, accounting for the precise mass, spin, and charge of the black hole, just to figure out where a particular photon came from. And the universe contains an enormous number of black holes. The Milky Way alone is estimated to harbor somewhere between 10 million and 1 billion stellar mass black holes, in addition to the supermassive black hole at its center, Sagittarius A star, which contains a mass equivalent to roughly 4 million suns squeezed into a region smaller than our solar system. Now, most of those black holes are not going to be directly in your path through deep space, but galaxy clusters, which a sufficiently long-range spacecraft would inevitably pass near or through, contain concentrations of mass, both in their luminous components and in their far larger dark matter halos, sufficient to cause measurable gravitational lensing of background objects. A spacecraft trying to navigate by stellar positions while transiting a galaxy cluster would find that the apparent positions of background stars and galaxies are subtly but measurably distorted relative to any pre-departure catalogue. and correcting for those distortions would require knowing the mass distribution of the cluster in detail, which takes us right back to the dark matter problem. There is another wrinkle in the geometry of deep space navigation that I want to bring in here, because it is perhaps the most elegant example of the universe's resistance to being navigated, and it comes from asking a deceptively simple question: what is a straight line in space? In flat Euclidean geometry, the geometry of a coordinate grid, the geometry you draw on paper, a straight line is the shortest distance between 2 points. Simple, intuitive, unambiguous, but in curved space-time, the generalization of a straight line is a geodesic, the path that extremizes the distance between 2 points, according to the metric of the spacetime you're in. And in a universe where the metric, the mathematical description of how distances are measured, is shaped by the distribution of mass and energy everywhere in space, geodesics can look very different from what your intuition would call straight. Consider a journey across a significant fraction of the universe. The spacecraft leaves from Earth, heading for some distant galaxy. The path it follows, the geodesic through spacetime, is influenced by every concentration of mass it passes near along the way. Galaxy clusters pull it slightly off course. The large-scale structure of the cosmic web, those vast filaments and sheets of matter, woven through with dark matter, creates subtle gravitational gradients that nudge the spacecraft's trajectory in ways that depend on the precise distribution of all that invisible mass. Over millions of light years, those tiny nudges accumulate into significant deviations. The spacecraft's actual path through space diverges from the path a navigator using only flat space geometry would have predicted. And here is the profound part. From the spacecraft's own reference frame, it is always going straight. It is always following the straightest possible path through the space-time it finds itself in. The deviation is not felt as a force. It is not registered by onboard accelerometers. It is simply the shape of the space the craft is moving through, silently redirecting the journey without any sensation of turning. A navigator aboard that spacecraft, relying on inertial measurements alone, would have no way to distinguish between "I went straight and arrived where I expected," and "I went straight through curved space and arrived somewhere unexpected." This is not a theoretical edge case. This is the default condition of travel through a universe filled with unevenly distributed matter and dark matter, threaded with gravitational fields that no complete map has ever charted. Straight lines in our universe are not what they appear, and over large enough distances, that gap between appearance and reality becomes impossible to ignore. At this point, I want to bring in something personal, because everything we've been discussing, the curvature of space, the topology of the universe, the bending of light around mass, can start to feel abstract, mathematical, removed from the lived experience of being a conscious creature asking questions about the cosmos. But consider what it actually means that you are here, in this moment, able to ask these questions at all. The atoms in your body were forged in the cores of stars that lived and died before the solar system existed. The carbon in your cells, the oxygen in your blood, the calcium in your bones, all of it was produced by nuclear fusion in stellar interiors, scattered across space in supernova explosions, gathered by gravity into clouds, condensed into a new star and its surrounding planets, and eventually, through billions of years of chemistry and biology and evolution, assembled into something capable of wondering about the shape of the universe it came from. You are the universe examining itself. You are stardust that has become curious. And the fact that you find navigating this universe difficult, that the geometry resists your intuition, that the distances exceed your imagination, that the physics defies your common sense, is not a failure. It is an invitation to go deeper, to think harder, to build better tools and better theories and better questions. Carl Sagan said it beautifully. We are a way for the cosmos to know itself, and knowing itself, it turns out, involves confronting its own strangeness, its own depth, its own resistance to easy answers. The shape of the universe is unknown, the nature of dark matter is unknown, the true value of the Hubble constant is disputed, the topology of spacetime on the largest scales is unmapped. And yet, here we are, not paralyzed by the uncertainty, but energized by it, building spacecraft, launching telescopes, spinning up quantum sensors in microgravity, listening to the radio whispers of dying stars, asking the universe over and over again, in every language of measurement we can devise, where are we? What are you? How do we find our way? That drive, that insatiable, restless, deeply human drive to navigate and understand, may be one of the most important things about us. Not because it guarantees answers, but because it keeps generating better and better questions. And speaking of better questions, I want to bring up one that has been lurking in the background of this entire conversation. One that doesn't get asked often enough, because it sounds almost philosophical rather than scientific, but it has genuine scientific content, and it cuts right to the heart of what we mean by finding your way home. The question is this: is home a place, or is it a moment? Think about what we mean when we say we want to return to Earth. We mean we want to get back to that specific rocky planet orbiting that specific star. But that planet is moving. It orbits the Sun at roughly 29.5 kilometers per second. The Sun orbits the galactic center at roughly 220 kilometers per second. The Milky Way moves through the local group. The local group moves through the Virgo supercluster. Everything is in motion all the time, at every scale. The Earth you left, if you've been traveling for decades, is not in the same place it was when you departed. Not remotely. It is hundreds of billions of kilometers from where it was. Its position in the galaxy has shifted. The solar system has moved. The galaxy has rotated. To return to Earth, you don't just need to know where it was. You need to know where it will be when you arrive, accounting for all of those motions compounded across however long the journey takes. This is actually something we handle quite well for missions within the solar system. Interplanetary navigation already requires predicting where a planet will be years in the future. That's how we calculate launch windows and gravity assist trajectories. But extending that kind of prediction across light years, over decades or centuries of travel, while accounting for the full complexity of gravitational influences from every massive object along the way, that is a problem of a different order entirely. The precision required grows exponentially with distance and time. The uncertainty in the final position grows with every variable you cannot measure perfectly. And in a universe with dark matter you cannot see, space-time curvature you cannot fully map, and an expansion rate you cannot pin down to everyone's agreement, the unpredictable variables are not small. Home is a moving target, a precise, specific, improbably small moving target, a rock 8,000 kilometers across, moving at nearly 30 kilometers per second around a star, in a galaxy rotating at hundreds of kilometers per second, in a universe expanding at a rate that is still being argued about. Finding it from deep space without a continuous connection to the navigational infrastructure we've built around our home planet is not just technically difficult, it is one of the most precisely beautiful problems the universe has ever posed to a thinking mind. Let's be honest about what the physics actually allows and what it doesn't. This is where things get truly wild and truly rigorous. Don't move. Let me say something right at the start of this part that I think is important. Everything we're about to discuss, wormholes, exotic matter, space-time manipulation, is real physics. I don't mean real in the sense of confirmed and observed and ready to be engineered. I mean real in the sense that these concepts emerge directly from the mathematics of general relativity the same framework that correctly predicted gravitational waves, black holes, the expansion of the universe, and the bending of light around massive objects. These are not the inventions of science fiction writers, even if science fiction writers have embraced them enthusiastically. They are solutions to Einstein's equations. They are what the mathematics allows, or at least, what it doesn't immediately forbid. And that distinction between what the equations permit and what the universe actually contains is where some of the most exciting and unresolved debates in modern theoretical physics are happening right now. So let's go there, carefully, honestly, with the same rigor we've applied to everything else in this conversation. The story begins, as so many stories in modern physics do, with Einstein. In 1915, Einstein published his general theory of relativity, a set of 10 coupled, nonlinear partial differential equations relating the geometry of spacetime to the distribution of mass and energy within it. These equations, known as the Einstein field equations, are among the most powerful and beautiful objects in all of mathematics. They encode an extraordinary amount of physics in a deceptively compact form, and they are hard. Genuinely, ferociously hard. So hard that in the century since Einstein published them, only a handful of exact solutions have ever been found. Solutions that describe specific, idealized physical configurations, simple enough that the mathematics can be solved analytically. One of the most famous of those exact solutions was found not by Einstein, but by a German physicist named Karl Schwarzschild, and he found it in 1916 while serving on the Russian front during the First World War. The Schwarzschild solution describes the geometry of spacetime outside a perfectly spherical, non-rotating, electrically neutral mass. It predicted the existence of what we now call black holes, regions where the curvature of spacetime becomes so extreme that nothing, not even light, can escape past the event horizon. Einstein himself was initially skeptical that such objects could actually exist in nature. He was wrong. Black holes are real, and we have now directly imaged two of them. The supermassive black hole at the center of the galaxy M87, first imaged by the Event Horizon Telescope collaboration in 2019, and Sagittarius A star, the supermassive black hole at the center of our own Milky Way, imaged by the same collaboration in 2022. Both images, fuzzy, orange, ring-shaped glows surrounding a dark central shadow, represent one of the greatest observational achievements in the history of astronomy. But there is something else hiding in the Schwarzschild solution. Something that Schwarzschild himself probably didn't notice, and that wasn't fully understood until decades later. When you extend the mathematical solution to its full form, when you include all of the regions of spacetime that the equations describe, not just the ones physically accessible from outside, you find that the black hole has a kind of mirror image on the other side. Another region of spacetime, connected to ours through the interior of the black hole, but completely separate and unreachable by any signal or traveler that enters the black hole. In 1935, Einstein himself and his colleague Nathan Rosen studied this feature of the solution and described it formally. The structure they described became known as an Einstein-Rosen bridge. Today, we call it a wormhole. A wormhole, in its simplest mathematical description, is a tunnel through space-time, a connection between two separate regions of the universe, or potentially between two separate universes entirely, that provides a shortcut vastly shorter than the path through ordinary space. Imagine folding a piece of paper and poking a pencil through it. The 2 points where the pencil enters and exits are far apart on the flat surface of the paper, but the pencil itself, traveling through the fold, connects them directly. A wormhole is the three-dimensional space-time equivalent of that pencil hole. In principle, A wormhole could connect 2 points in the universe separated by billions of light years, while the passage through the wormhole itself might be only meters or kilometers long. In principle, a wormhole could be used to travel from one side of the galaxy to the other in moments. In principle, a wormhole would solve the deep space navigation problem in the most dramatic way imaginable, not by getting better at navigating the distances, but by eliminating the distances entirely. And here is where we have to be rigorously, painstakingly honest. Because the gap between the mathematics permits this, and you can actually use this, is in this case enormous. The Schwarzschild wormhole, the one that appears naturally in the full mathematical extension of the black hole solution, is not traversable. You cannot travel through it. It is what physicists call a maximally extended Schwarzschild solution, and in that solution, the wormhole exists only for an infinitesimally brief moment before collapsing. The throat of the wormhole pinches off faster than any signal or traveler could cross it. Even light cannot get through before the geometry closes. The Einstein-Rosen bridge is a mathematical feature of the solution, not a physical tunnel you could fly a spacecraft through. For a wormhole to be traversable, for it to stay open long enough for something to pass through, it would need to be threaded with something that general relativity calls exotic matter. Exotic matter is not just unusual or rare matter, it is matter with a negative energy density, matter that, in a region of space, has less energy than empty vacuum. This property, sometimes described as having negative mass, though that's a slight oversimplification, would gravitationally repel rather than attract, providing the outward pressure needed to hold the wormhole throat open against the natural tendency of the geometry to collapse. Does exotic matter exist? This is genuinely one of the most important open questions in physics, and the answer is, maybe, in a limited sense, under very specific circumstances, there is a real, experimentally confirmed quantum phenomenon called the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and measured in the laboratory for the first time in 1997 by Stephen Lamoureux. Place 2 perfectly flat, uncharged metal plates very close together in a vacuum, within a few hundred nanometers, and quantum mechanical fluctuations in the electromagnetic field create a net attractive force between them. The space between the plates has a slightly lower energy density than the surrounding vacuum. In a precise technical sense, the region between the plates exhibits a negative energy density relative to empty space. This is real. It has been measured. It is not controversial, but, and this is a very large but, the magnitude of the Casimir effect is extraordinarily small. The force between the plates is tiny. The negative energy density produced is minuscule. Scaling this effect up to the quantities that would be needed to hold open a traversable wormhole large enough for a spacecraft, or even for a single particle, would require conditions so extreme that they lie far beyond anything remotely conceivable with current or foreseeable technology. Some calculations suggest the negative energy required would be comparable to the total mass energy of a planet or a star, generated and maintained in a region of space just large enough for a spacecraft to pass through. In 2023, a team at Caltech published a landmark paper in the journal Nature describing a quantum gravity experiment performed on Google's Sycamore quantum computer. The team, led by physicist Maria Spyropoulou, created a quantum system that simulated the transmission of information through a wormhole, using quantum entanglement to teleport a quantum state between 2 regions of the quantum processor in a way that was consistent with the expected behavior of a traversable wormhole in a simplified theoretical model called Jaccard-Teitelbaum gravity. The paper generated enormous public excitement and a fair amount of scientific debate. It is important to be clear about what that experiment did and did not demonstrate. It did not create a physical wormhole. It did not tunnel anything through space-time. What it demonstrated was that a quantum information protocol, one inspired by the theoretical structure of wormhole physics, could be implemented on a quantum processor and produce results consistent with theoretical predictions. It was a proof of concept for a theoretical idea, implemented in a quantum simulation. Fascinating, rigorous, genuinely significant as a step in understanding the deep connections between quantum information theory and gravitational physics, but not a wormhole you could navigate. The connection between wormholes and quantum entanglement, the mysterious quantum mechanical phenomenon where two particles, once they've interacted, remain correlated in ways that cannot be explained by any local hidden variable, no matter how far apart they are, is itself one of the most exciting frontiers in theoretical physics. A conjecture known as ER equals EPR, proposed by physicist Juan Maldacena and Leonard Susskind in 2013, suggests that quantum entanglement and wormholes might be two descriptions of the same underlying phenomenon, that every pair of entangled particles is, in some deep sense, connected by a microscopic wormhole. If true, this would represent a profound unification of quantum mechanics and general relativity, the two great pillars of modern physics that have stubbornly resisted being merged into a single consistent theory for nearly a century. But even if ER equals EPR is correct, and it remains a conjecture, not a proven theorem, it does not immediately translate into a navigational tool. Quantum entanglement cannot be used to transmit information faster than light. This is a well-established result called the no communication theorem. You cannot use your entangled particles to send a message to someone on the other side of the galaxy instantaneously. The correlations between entangled particles are real, but they can only be revealed by comparing measurements, and that comparison requires a classical communication channel, which is limited by the speed of light. Entanglement is extraordinary. It is one of the most counterintuitive and well-verified features of quantum mechanics, but it is not a shortcut through space, at least not in any way we currently understand how to use. There is another class of proposed space-time shortcuts that deserves careful attention because it comes with a more concrete theoretical basis and has attracted serious study from mainstream physicists. It's called the Alcubierre drive, and it was proposed in 1994 by Mexican physicist Miguel Alcubierre in a paper published in the journal Classical and Quantum Gravity. The Alcubierre drive works, in theory, not by accelerating a spacecraft to high speeds, but by warping the spacetime around the spacecraft. The idea is to create a bubble of flat spacetime containing the ship, while contracting the spacetime in front of the bubble and expanding it behind. The net effect is that the bubble, and everything inside it, effectively moves through space at whatever speed the warp rate dictates, potentially faster than light, while the occupants inside the bubble experience no acceleration and no relativistic time dilation. From inside the bubble, everything feels normal. From outside, the spacecraft has covered an enormous distance in a very short time. This is geometrically possible within general relativity. Alcubierre showed the mathematics explicitly, and the concept is genuinely appealing from a navigation standpoint because it sidesteps many of the problems we've been discussing. No time dilation means no clock synchronization problem. No acceleration means no physiological stress on crew members. And in principle, the drive could be used in reverse to return home just as quickly as it was used to depart. But the practical obstacles are once again profound. The Alcubierre drive requires exotic matter, the same negative energy density material needed for traversable wormholes. Initial calculations suggested the amount needed was staggering, on the order of 10 to the power of 64 kilograms of negative energy, which is vastly more mass energy than the entire observable universe contains. Subsequent refinements have brought that number down significantly, with some proposals suggesting configurations that would require much less exotic matter, but still amounts utterly beyond any conceivable technology. There are also deeper problems. The Alcubierre drive, as originally formulated, requires the region of space-time being manipulated to be set up in advance, before the ship is inside the bubble, which means you would need some way to pre-configure the warp bubble at a destination you haven't visited yet. And inside the bubble itself, the spacecraft has no way to control or steer the drive, because no signals from inside the bubble can reach the bubble walls. The walls are moving faster than the signals. It's a bit like trying to steer a car when your hands are separated from the steering wheel by the speed of light. Physicist Harold White at NASA's Johnson Space Center spent several years exploring refined versions of the Alcubierre concept, looking for geometric configurations that might reduce the exotic matter requirements. His work, while serious and peer-reviewed, has not produced a design that overcomes the fundamental obstacles. The exotic matter requirement, even in its reduced form, remains far beyond anything we can produce or store, and the causality issues, the fact that faster-than-light travel in the framework of relativity is deeply connected to the possibility of traveling backward in time with all the logical paradoxes that entails, suggest that even if the engineering were somehow solved, the physics might impose prohibitive restrictions. I want to pause here and zoom out, because I think it's easy, when discussing concepts like wormholes and warp drives, to fall into one of two traps. The first trap is uncritical enthusiasm, treating these ideas as essentially solved engineering challenges, just waiting for the right budget and the right team. The second trap is dismissive skepticism, writing these ideas off as pure fantasy, of no relevance to serious scientific discussion. The truth, as it almost always is in physics, is more interesting than either extreme. These concepts are mathematically grounded. They are the subject of serious research by serious physicists at serious institutions. They appear in peer-reviewed journals. They have shaped our understanding of the deep structure of general relativity and its relationship with quantum mechanics. And they have taught us things about the universe that we would not have learned without exploring them rigorously. What they have not done, and what they may never do, is provide a practical pathway to deep space navigation. The obstacles, the exotic matter requirements, the causality constraints, the engineering impossibilities at every scale we can currently imagine are not minor hurdles. They are deep, possibly fundamental barriers. Whether they represent permanent walls or merely the current horizon of our understanding is something we genuinely don't know. Physics has surprised us before. It will almost certainly surprise us again. The history of science is littered with things that were once declared impossible: heavier than air flight, nuclear energy, gravitational wave detection. In 1888, physicist Heinrich Hertz demonstrated radio waves in his laboratory and declared in print that they would never have any practical application. 17 years later, Guglielmo Marconi sent a radio signal across the Atlantic Ocean. The universe has a habit of making fools of those who declare absolute limits on human ingenuity. And yet, and this is the honest part, the universe also has a habit of enforcing its own rules with perfect consistency. The speed of light has never been exceeded by any observed object or signal. The laws of thermodynamics have never been violated in any experiment. Conservation of energy has never failed. Some limits are not engineering challenges, they are features of reality itself. And the challenge, the genuinely hard, genuinely important intellectual challenge, is figuring out which category each apparent barrier falls into. Now, I want to bring in something that connects all of this back to navigation in a very direct way, because there is one phenomenon in modern physics that makes space-time shortcuts feel not just theoretically possible, but almost tantalizingly close to real. And that phenomenon was detected for the first time on September 14, 2015, a date that I would argue deserves to be ranked among the most significant in the history of science. Gravitational waves, Einstein predicted them in 1916, almost as an afterthought, a consequence of his field equations that he wasn't entirely sure were physically meaningful rather than mathematical artifacts. The idea is this: when massive objects accelerate, when they change their velocity or direction of motion, they disturb the fabric of space-time around them, sending ripples outward at the speed of light. These ripples are gravitational waves. They travel through the universe, stretching and squeezing the distances between objects as they pass, not by moving objects through space, but by momentarily altering the geometry of space itself. For 100 years after Einstein's prediction, gravitational waves remained undetected. Not because physicists doubted they existed. The indirect evidence was overwhelming, including the beautifully precise orbital decay of the Hulse-Taylor binary pulsar discovered in 1974, which earned Russell Hulse and Joseph Taylor the Nobel Prize in Physics in 1993, but because detecting them directly required measuring a distortion in the length of a 4-kilometer laser beam of less than 1,000th the diameter of a proton. That is a sensitivity almost beyond comprehension, and achieving it required decades of engineering refinement and the construction of the Laser Interferometer Gravitational Wave Observatory, LIGO, the most precise measuring instrument ever built by human hands. On September 14, 2015, LIGO detected a gravitational wave signal lasting approximately 0.2 of a second. Analysis of the signal revealed its source: two black holes, each roughly 30 solar masses, spiraling together and merging in a violent collision that released more energy in those final fractions of a second than all the stars in the observable universe combined, emitted as gravitational waves rather than light. The event had occurred approximately 1.3 billion light-years from Earth. The distortion it caused in the 4-kilometer LIGO arm was roughly 0.004 of a femtometer, smaller than the nucleus of an atom. That detection, announced to the world in February of 2016, opened an entirely new window on the universe, not a window of light, but a window of space-time itself, and it validated, in the most direct possible way, that space-time is not just a mathematical abstraction. It is a physical medium. It can be disturbed. It carries waves. It transmits information, not through electromagnetic radiation, but through the literal stretching and squeezing of the fabric of reality. Since that first detection, the LIGO and Virgo collaborations have catalogued hundreds of gravitational wave events, merging black holes, merging neutron stars, and events whose nature is still being debated. The detection of gravitational waves from a neutron star merger in 2017, an event designated GW 170817, was accompanied by a gamma-ray burst detected by the Fermi and Integral Space Observatories, confirming that gravitational waves and light from the same event arrive at Earth at essentially the same time. The speed of gravitational waves equals the speed of light, to within 1 part in 10 to the 15th. That single measurement ruled out entire classes of alternative gravity theories that had been taken seriously for decades. It is, by any measure, one of the most precise experimental results in the history of physics. What does this have to do with navigation? In two ways that I find genuinely exciting. First, gravitational waves carry information about their source, the masses, spins, and distances of the objects that generated them, encoded in the pattern of the wave. As gravitational wave astronomy matures and our detector networks improve, with planned future detectors like LISA, the Laser Interferometer Space Antenna, a space-based gravitational wave observatory currently under development by the European Space Agency and scheduled for launch in the mid-2030s. We will build up a gravitational wave map of the universe, a map not of light but of space-time disturbances, a map that in principle a sufficiently advanced navigator could use to triangulate position by detecting and characterizing the gravitational wave background. The constant, overlapping hum of gravitational waves from countless sources throughout the universe. This stochastic gravitational wave background has already been tentatively detected by pulsar timing arrays, which measure tiny fluctuations in the arrival times of pulsar signals caused by passing gravitational waves. Second, and more speculatively, the existence of gravitational waves as a physical phenomenon reminds us that space-time is dynamic. It moves, it responds, it carries energy, and a medium that can carry waves is a medium that in principle can be shaped, manipulated, and interacted with. Not easily, not with any technology we can currently imagine, but in principle. And in physics, what is permitted in principle tends, given enough time and ingenuity, to eventually become possible in practice. Whether that principle ever translates into a practical navigation tool, whether the ripples of space-time might one day serve as the landmarks of a cosmic map, is something no one can currently say with confidence. But it is a question being asked, seriously and rigorously, by people who build the most sensitive instruments ever conceived. And that is exactly where questions about the future of navigation should be asked. I want to close this part with something that ties together the theoretical and the deeply personal, because the concepts we've explored today, wormholes, exotic matter, warp bubbles, gravitational waves, might sound like the domain of equations and laboratories far removed from the human experience of wondering what's out there. But they are not. They are the leading edge of a species-wide conversation about what kind of universe we live in, what it will allow us to do, and how far we can ultimately reach. Every civilization that has ever looked up at the stars has imagined reaching them. The Greeks placed their gods on Olympus and their heroes among the constellations. The Polynesian navigators crossed the largest ocean on Earth by reading the sky with their bodies as well as their eyes. The astronomers of the Islamic Golden Age, working in the observatories of Baghdad and Samarkand 1,000 years ago, laid the mathematical foundations that Newton and Einstein would later build upon. The engineers at NASA and ESA and JAXA and every other space agency on Earth are the latest generation in an unbroken chain of humans who refuse to accept that the horizon was a wall. Whether we ever solve the deep space navigation problem, whether we ever find a way to travel to another star and find our way home, we will not do it by dismissing the obstacles. We will do it by understanding them, by mapping the curvature of space-time, by cataloguing the pulsars, by building the quantum sensors, by detecting the gravitational waves, by asking the equations what they permit, and then finding out whether the universe agrees. We are made of the same stuff as the stars we're trying to reach. And that, I think, gives us more than a reason to try. It gives us a kind of right, a cosmic inheritance. The universe built us out of itself, gave us curiosity and mathematics, and the ability to wonder, and then set us loose in a cosmos that is vast and curved and dark and expanding and beautiful beyond all ordinary description. Finding our way home from deep space might be impossible with the tools we have today, but the universe is old, and we are just getting started. There is a question that sits underneath all of physics, underneath all of cosmology, underneath every equation, every observation, every experiment ever designed and conducted by a human mind. And it is not a question about any specific phenomenon or any particular measurement. It is a question about the nature of reality itself, about what the universe fundamentally is, at the deepest level we can probe. The question is this: Is the universe made of things, or is it made of information? That might sound like a philosophical question dressed up in scientific language, but it isn't. It is a genuine, active, intensely debated question at the frontier of theoretical physics. And the reason it matters for deep space navigation, the reason I'm bringing it up here, in the middle of a conversation about getting lost in the cosmos, is that if the universe is, in some deep and fundamental sense, informational in its nature, then the universe itself might contain something like an address system, a built-in structure that encodes location and relationship in a way we haven't yet learned to read. Let me take you through the physics carefully, because this is one of those areas where the gap between the popular account and the actual science is large, and I want to make sure we stay on the right side of that gap. It begins with black holes. Again, these extraordinary objects keep appearing at the frontier of physics precisely because they are the places where all of our theories get pushed to their absolute limits, where gravity is strongest, where space-time curvature is most extreme, where the clash between general relativity and quantum mechanics is most acute. In the 1970s, physicist Stephen Hawking made a discovery that shook the foundations of theoretical physics. Using a combination of general relativity and quantum field theory, two frameworks that are notoriously difficult to reconcile, he showed that black holes are not completely black. They emit radiation. Quantum mechanical processes near the event horizon cause pairs of particles to spontaneously appear, one falling into the black hole, the other escaping as radiation. This Hawking radiation, as it became known, carries energy away from the black hole, causing it to slowly lose mass and, over an astronomically long timescale, eventually evaporate entirely. This was a stunning result, but it came with a devastating implication. If a black hole evaporates completely, what happens to all the information about everything that ever fell into it? The matter, the radiation, the quantum states of every particle, all of it apparently is gone, destroyed, erased from the universe. And this is a catastrophic problem, because one of the deepest principles in quantum mechanics, one that has never been observed to be violated in any experiment, is that information is conserved. Quantum states evolve in ways that are reversible. If you know the final state of a quantum system with perfect precision, you can, in principle, reconstruct its entire history. Information cannot be created or destroyed, it can only be transformed. So if a black hole destroys information, if it takes in quantum states and converts them to featureless Hawking radiation with no memory of what fell in, then quantum mechanics is violated. One of the two greatest theories in modern physics breaks down. This tension became known as the black hole information paradox, and it has been one of the most productive sources of theoretical physics research for the past 5 decades. The resolution that has emerged, tentatively, and not without ongoing debate, points towards something called the holographic principle. And the holographic principle, if it is correct, changes everything about how we think about information, space, and reality. The holographic principle originated in the work of physicists Gerard Hooft and Leonard Susskind in the early 1990s. The core idea is this: all of the information needed to describe everything that happens within a volume of space is encoded on the surface that bounds that volume, not in the volume itself, on its surface. Like a hologram, where a 3-dimensional image is encoded in a 2-dimensional pattern of interference fringes, the 3-dimensional content of a region of space might be fully described by a 2-dimensional map on its boundary. Applied to a black hole, this means that all the information about everything that ever fell into the black hole is encoded on the event horizon, the 2-dimensional surface that marks the boundary of the black hole, rather than being destroyed within the singularity. The Hawking radiation, as it's emitted, carries this information away in subtle quantum correlations that are incredibly difficult to decode, but are, in principle, present. Information is not destroyed. It is transformed and relocated to the boundary. In 1997, Argentine-American physicist Juan Maldacena published what has become one of the most cited papers in the history of physics. In it, he proposed a precise mathematical correspondence between a theory of gravity in a particular curved space-time, specifically anti-de Sitter space, a hypothetical universe with a negative cosmological constant, and a quantum field theory living on the boundary of that space-time with no gravity at all. This correspondence, known as the AD-SCFT duality or the Maldacena conjecture, provides the first concrete, mathematically precise realization of the holographic principle. In this framework, the three-dimensional gravitational physics happening in the bulk of the space-time is exactly equivalent to, perfectly dual to, a two-dimensional quantum theory living on its boundary. Every event, every particle, every gravitational wave in the interior has a precise description in terms of the boundary theory. The two descriptions are not approximations of each other. They are mathematically the same thing viewed from different perspectives. Now, what does this have to do with navigation? Let me draw the connection carefully, because it is subtle but genuinely profound. If the holographic principle is correct, if it applies not just to the specific mathematical setting of AD-SCFT, but to the real universe we inhabit, then the universe might have a kind of built-in address system. Information about every location in the three-dimensional interior of the universe is encoded on a two-dimensional surface. The geometry of space itself, the distances, the relationships, the positions of every object, might emerge from patterns of quantum entanglement on a surface rather than being a fundamental feature of reality. Space, in this picture, is not a pre-existing stage on which physics happens. It is something that arises from and is encoded in a more fundamental level of reality. This idea, sometimes called the emergence of space-time from quantum entanglement, is one of the most active research frontiers in theoretical physics right now. The work of physicists like Mark van Ramsdonk, who showed in 2010 that entanglement between regions of the boundary theory is directly connected to the geometric connectivity of the bulk space-time, suggests that the fabric of space is literally woven from quantum correlations. Remove the entanglement and the space-time tears apart. Increase it and distant regions become geometrically closer. If you could read the holographic encoding of space-time, if you could decode the information on the boundary and reconstruct the geometry of the interior, you would, in principle, have a complete map of the universe, every location, every distance, every relationship, a perfect navigational chart encoded in the quantum structure of reality itself. Of course, and I want to be very clear about this, we have no idea how to read that encoding. We don't know if the real universe has a boundary in the relevant sense. We don't know if the holographic principle applies to a universe with a positive cosmological constant, which is what we actually live in the same rigorous way it applies in AD-SCFT. These are open questions, big ones, but they point toward a possibility that is, I think, one of the most breathtaking in all of science, that the universe is not just a place you navigate, it is a structure that encodes its own map, and finding a way to read that map might be one of the defining achievements of whatever physics looks like 1,000 years from now. Let's come down from that altitude for a moment and talk about something more concrete, something that also lives at the frontier of observation and theory, but that has a direct, physical presence in the universe, rather than living purely in the mathematics of boundary theories. I'm talking about cosmic strings. Cosmic strings are hypothetical, one-dimensional topological defects in the fabric of space-time, long, infinitely thin tubes of concentrated energy that might have formed in the early universe during phase transitions in the first fractions of a second after the Big Bang. Think of them by analogy with what happens when water freezes into ice. As water cools through its freezing point, ice crystals form and grow in different places simultaneously. When those crystals meet, they don't always align perfectly. The boundaries between misaligned crystal domains form defects in the ice structure. The universe, as it cooled from its initial extraordinarily hot state, may have undergone similar phase transitions, and the boundaries between regions that transition differently might have formed topological defects in the fabric of spacetime itself. Cosmic strings would be one type of such defect. If cosmic strings exist, they are remarkable objects. They would be unimaginably thin, far smaller than a proton in cross-section, but incredibly dense. A single centimeter of cosmic string might contain a mass comparable to millions of tons. Their gravitational properties would be unusual. A cosmic string doesn't attract matter toward it in the way a normal massive object does. Instead, it creates a conical distortion in the spacetime around it, removing a wedge-shaped section of space and causing two parallel lines passing on either side of the string to converge. This creates a characteristic double image effect. Light from a source behind a cosmic string would appear as two identical images, side by side, without the circular arcs or rings you'd see from gravitational lensing by a spherical mass. Astronomers have looked for cosmic strings through their gravitational lensing signatures and through their expected imprint on the cosmic microwave background. A characteristic pattern of temperature discontinuities along the string's path across the sky. So far, no confirmed detection. Some candidate observations been made, including a pair of galaxies designated CSL-1, observed in 2003, that produced a double image consistent with cosmic string lensing. But subsequent observations suggested the two images were more likely a pair of nearly identical elliptical galaxies rather than a lensing artifact. The search continues. Why do cosmic strings matter for navigation? Because if they exist, they are among the most extreme structural features the universe could contain. Loops of cosmic string, vibrating and radiating gravitational waves, would leave a distinctive signature in the stochastic gravitational wave background, one that next-generation gravitational wave detectors, including pulsar timing arrays and eventually LISA, might be able to detect. And a universe threaded with cosmic strings would have a large-scale structure shaped in part by those strings, with matter clustering along them in characteristic patterns that could, in principle, serve as navigational landmarks at cosmological scales. More speculatively, the conical geometry around a cosmic string has been proposed as a mechanism for achieving closed time-like curves, paths through space-time that loop back on themselves in time. Two cosmic strings passing near each other at relativistic speeds could, according to some solutions of Einstein's equations, create a region of space-time in which this looping is possible. This is deeply controversial, and if it leads to genuine time travel paradoxes, likely indicates that such solutions cannot occur in the real universe, perhaps prevented by some as yet unknown quantum gravity effect. But the fact that the equations permit it is, once again, a reminder of just how strange and rich the geometry of space-time can be when you push it to its limits. I want to spend a few minutes on something that is perhaps the deepest unresolved question relevant to everything we've been discussing throughout this entire conversation. The question of quantum gravity. Because every time we've run into a fundamental barrier, every time the physics has refused to give us a clean answer, we've ultimately arrived at the same underlying problem. We have two extraordinarily successful theories of physics: quantum mechanics, which describes the behavior of matter and energy at the smallest scales with a precision that is, by some measures, the most accurate in the history of science. And general relativity, which describes gravity and the large-scale structure of space-time with a precision that has been confirmed in every experiment ever designed to test it. And these two theories are fundamentally incompatible. They cannot both be exactly right, because the assumptions underlying each one are inconsistent with the assumptions underlying the other. Quantum mechanics is built on the idea that physical quantities are discrete, probabilistic, and defined only through the act of measurement. General relativity is built on a smooth, continuous space-time that evolves deterministically according to the field equations. Quantum mechanics treats space-time as a fixed background on which quantum fields play out. General relativity says space-time is dynamic, shaped by the matter and energy it contains. You cannot simply combine these two frameworks without resolving their foundational contradictions, and doing so requires a theory of quantum gravity, a description of how the quantum world and the gravitational world fit together at the smallest possible scales. The smallest possible scale in this context is the Planck length, approximately 1.6 times 10 to the power of minus 35 meters. At that scale, unimaginably smaller than a proton, which is itself roughly 10 to the power of minus 15 meters across, the quantum fluctuations of space-time geometry are expected to become significant. Space itself is thought to become foamy, fluctuating, probabilistic. The smooth, continuous fabric of general relativity dissolves into something granular and uncertain. And what exactly that granular space-time looks like, what the quantum structure of space and time actually is something no current theory fully describes. The leading candidates for a theory of quantum gravity are string theory and loop quantum gravity. String theory, the idea that the fundamental constituents of nature are not point particles but one-dimensional vibrating strings, whose different vibrational modes correspond to different particles, naturally incorporates gravity and provides the mathematical framework for ADS-CFT. Loop quantum gravity, developed by physicists including Carlo Rovelli and Lee Smolin, quantizes space-time geometry directly, describing space as built from discrete finite chunks called spin networks with a minimum possible area equal to the Planck area. Both approaches have had significant successes and significant struggles. Neither has yet produced a prediction that has been confirmed by experiment in a way that rules out the other. The energies required to directly probe Planck-scale physics are so far beyond any particle accelerator we could conceivably build that direct experimental tests of quantum gravity have long seemed impossible. But there are indirect probes, signatures in the cosmic microwave background, in the polarization of high-energy gamma rays from distant sources, in the precise timing of gravitational wave signals, that might, with sufficient precision, reveal hints of the quantum structure of space-time. For navigation, for understanding what it means to move through space at the most fundamental level, a theory of quantum gravity matters enormously. Because if space is discrete at the Planck scale, then position itself is not a continuous variable. The concept of being at a precise location in space might not be meaningful below a certain scale. The notion of a trajectory, a smooth path through space-time from one point to another, might break down at small enough scales and require replacement with something more probabilistic, more quantum, more alien to our intuition than anything we've discussed so far. Whether that quantum fuzziness of space-time matters for the kind of large-scale navigation we've been talking about, whether it has any practical effect at the scale of spacecraft and star systems and galaxies, is unclear. The Planck length is so extraordinarily small that its effects are utterly negligible at human scales. But at the extreme conditions near black hole singularities, or in the first instance of the universe's existence, quantum gravity effects become dominant. And understanding those extremes is essential to understanding the universe's full structure, including, ultimately, the large-scale geometry within which any navigation must take place. There is one more idea I want to introduce in this part, because it sits at the intersection of quantum gravity, information theory, and the navigation problem in a way I find genuinely beautiful. It is called the holographic entropy bound, and it was formulated by physicist Jacob Bekenstein in the 1970s, initially in the context of black hole thermodynamics. Bekenstein showed that the maximum amount of information that can be contained within any region of space is proportional to the surface area of that region, not its volume. Specifically, the maximum entropy, the maximum number of distinguishable physical states of any region is equal to 1/4 of the surface area of its boundary, measured in Planck units. This is called the Bekenstein bound, and it is one of the deepest results in theoretical physics. The implication is striking. The information content of a region of space is limited by its boundary, not its interior. No matter how much matter and energy you pack into a given volume, the total number of distinct states it can occupy, the total information it can contain, cannot exceed the area of the surface surrounding it. Measured at the Planck scale, reality, in some deep sense, is less informationally dense than it appears. The universe contains less information than a naive count of its volume would suggest. Now here is the navigational implication I want you to sit with. If the information content of any region of space is finite, bounded by its surface area, then the universe contains a finite amount of information about the positions and states of everything within it. The universe is not infinitely detailed. It is at some fundamental level a finite informational structure. And a finite informational structure, while it may be incomprehensibly large, is in principle fully describable, in principle readable, in principle mappable. The challenge of deep space navigation is, at its deepest level, a challenge of reading a finite but astronomically complex informational structure under conditions of severe measurement limitation, relativistic time dilation, cosmic expansion, and fundamental quantum uncertainty. The map exists encoded in the quantum state of the universe itself. The problem is that we don't yet know the language it's written in. Learning that language, developing the theoretical and technological tools to read the universe's own informational structure, may be the navigation challenge not of this century, but of the next 1,000 years of human scientific development. And I find that genuinely exciting, not frustrating, not discouraging, exciting, because it means the problem is not hopeless. It means there is something to find. The universe is not an infinite fog of unknowable complexity. It is a finite, structured, physically lawful system, and physical systems that are finite, structured, and lawful can, at least in principle, be understood. We just need more time, more curiosity, more of the patient, rigorous, endlessly creative work that science actually is when it's operating at its best. Let me bring us back to something human for a moment, because I think we've been in the mathematics long enough to need a breath of warm air. Think about the first humans who looked up at the night sky and tried to make sense of what they saw. No telescopes, no mathematics beyond the most basic counting and geometry, no concept of galaxies or black holes, or quantum entanglement, or holographic entropy bounds. Just eyes and brains and the relentless, aching human need to understand. They saw patterns in the stars and named them after animals and gods and heroes. They tracked the movements of the planets and built calendars that let them predict the seasons. They used the constellations to navigate across deserts and oceans. They made enormous structures, Stonehenge, the pyramids of Giza, the ancient observatories of Mesoamerica, aligned with celestial events in ways that required decades of careful observation and sophisticated mathematical reasoning. They were doing the best they could with what they had, and what they had was far less than what we have now, and yet the navigational and astronomical knowledge they built up, the star charts, the planetary tables, the calendars, the mythological frameworks that encoded observations across generations, was not wrong in the way that matters most. It was incomplete. It was a beginning. It was the first few sentences of a conversation that is still ongoing, still deepening, still surprising everyone who pays attention to it. We are further along in that conversation than any of those ancient observers could have imagined. We have mapped the cosmic microwave background to extraordinary precision. We have detected gravitational waves from black hole mergers 1 billion light-years away. We have imaged the shadow of a supermassive black hole. We have landed robots on Mars and dropped a probe through the clouds of Titan and collected material from an asteroid and brought it home to study in a laboratory. We have done things that would have seemed not just impossible but literally inconceivable to the people who built Stonehenge, and we are still, by every honest measure, at the very beginning. The universe is 13.8 billion years old. Modern science, in anything resembling its current form, is perhaps 500 years old. We have been asking rigorous, mathematically precise questions about the cosmos for a tiny fraction of its history. The idea that we have reached the limits of what can be known, that the navigation problem is permanently, absolutely, forever beyond us, seems in that light extraordinarily premature. The universe is vast, it is curved and dark and expanding and full of invisible matter and mysterious energy. It is governed by physics that our best theories still cannot fully reconcile, and it contains, encoded in its own quantum structure, a map of itself that we have only just begun to suspect exists. Finding your way home in deep space might be impossible today, with the tools of today, with the understanding of today. But today is not forever, and the cosmos, patient and ancient and indifferent as it is, has been waiting for the right questions for 13.8 billion years. We are, right now, in this generation, with these telescopes and these equations and these minds, asking some of the right questions for the very first time. This is where that conversation about generation ships becomes very, very relevant. If you haven't seen the video we did on the brutal truth about living aboard a generation ship, now would be a very good time to go watch it, because everything we cover there feeds directly into what we're about to discuss. The link is on screen and in the description. But stay with me first, because now is where the theory meets the mission. Let's talk about what it would actually take to leave, not in the abstract, not in the language of equations and theoretical frameworks and mathematical solutions to Einstein's field equations. In the concrete, engineering, how do you actually build this sense? Because everything we've discussed so far, the expanding universe, the curvature of space-time, the holographic principle, the limits of light as a navigation tool, all of it becomes suddenly, viscerally real the moment you start trying to design a spacecraft that could actually reach another star system and, crucially, find its way back. There are real proposals on the table right now, not science fiction, not speculative hand-waving, real proposals backed by real money, real science and real engineering teams working on real problems. And examining those proposals, understanding what they can do and where they break down, tells us more about the deep space navigation problem than any amount of purely theoretical discussion. Because the navigation problem is not just a physics problem, it is an engineering problem, a biology problem, a communication problem, and a profoundly human problem, all tangled together in ways that don't come apart cleanly. So let's go through the serious proposals, let's look at what each one actually involves. And let's be rigorously honest about where each one runs into the navigation challenges we've been mapping throughout this conversation. The first proposal I want to discuss is the one that has received the most attention in recent years, and the one that is, in some ways, the most technically serious near-term candidate. It's called Breakthrough Starshot, and it was announced in April of 2016 by physicist Stephen Hawking, entrepreneur Yuri Milner, and Facebook founder Mark Zuckerberg. With an initial commitment of $100 million for research and development, the concept is elegant in its simplicity, which is part of why it's taken seriously. Instead of trying to accelerate a large, crewed spacecraft to a significant fraction of the speed of light, a task that runs immediately into the enormous energy requirements imposed by special relativity, Breakthrough Starshot proposes to send thousands of extremely small, extremely lightweight spacecraft, each one no bigger than a postage stamp, called star chips. Each star chip would be a fully functional spacecraft, carrying a camera, navigation sensors, a communication laser, and power supply, all integrated into a gram-scale wafer using the same miniaturization technologies that have made modern smartphones possible. Each star chip would be attached to a similarly tiny light sail, a thin reflective membrane perhaps a few meters across, with a total mass of only a few grams. The propulsion concept is the crucial part. Rather than carrying any propellant, the star chips would be accelerated by a ground-based laser array, a phased array of lasers on Earth's surface, with a combined output power of perhaps 100 gigawatts, focused onto the light sail of each star chip in turn. The radiation pressure of the laser light pushing against the light sail would accelerate each star chip to approximately 20% of the speed of light, roughly 60,000 kilometers per second, within a few minutes of laser exposure. At that speed, the journey to Alpha Centauri, our nearest stellar neighbor at approximately 4.2 light-years distance, would take roughly 20 years. This is a genuinely serious proposal. The physics of laser propulsion via light sails is well understood. The engineering challenges, building a phased laser array of sufficient power, constructing light sails thin and reflective enough to achieve the required acceleration without being destroyed, miniaturizing a complete spacecraft to gram scale while maintaining functionality, are immense but are not obviously impossible. Research groups around the world have been working on each of these components since 2016, with meaningful progress on several fronts. Prototype wafer-scale spacecraft have been built and tested in space. Lightweight reflective sail materials have been fabricated and tested. The laser array concept has been refined in theoretical studies. Now, what does Breakthrough Starshot look like from a navigation perspective? The targeting problem alone is formidable. Alpha Centauri is 4.2 light-years away. The star chip will be traveling at 20% of the speed of light, and once the laser array is no longer illuminating its sail, which happens within minutes of launch, there is no further propulsion. The star chip is a ballistic projectile. It cannot steer, it cannot correct its course, it cannot compensate for any error in its initial trajectory. The targeting precision required to ensure the star chip passes through the Alpha Centauri system rather than missing it entirely after a 20-year, 42 trillion kilometer journey on a trajectory set in the first few minutes after launch is extraordinary. Any deviation from the planned trajectory caused by the laser array's pointing errors, manufacturing imperfections in the sail, the solar wind, the gravitational influence of bodies in the outer solar system, or any other perturbation will grow over 20 years into a potentially enormous positional error at the destination. There is no mid-course correction capability. There is no propulsion system that can be used during the cruise phase. The only navigation option available is passive, using onboard sensors to measure the positions of stars and make tiny adjustments using differential radiation pressure on asymmetric sail configurations. or perhaps using attitude control thrusters powered by an onboard power source. But the delta V, the change in velocity, available from such methods is negligibly small compared to the cruise velocity of 60,000 kilometers per second. The Starship will go where it's aimed at launch. The precision of that aiming is everything. At the destination, the situation is more interesting, but no less challenging. Moving at 20% of the speed of light, the Starship will pass through the Alpha Centauri system in a matter of hours, perhaps less. There is no deceleration capability. There is no way to slow down. The flyby is brief, the opportunity to observe and image the system is fleeting, and the data collected during that narrow window must then be transmitted back to Earth using a tiny onboard laser. At 4+ light-years distance, transmitting enough data to be useful from a gram-scale power source is another significant engineering challenge. And returning? There is no return. A 20% of light-speed Starship, once launched, is gone. It has no deceleration capability, no way to turn around, no way to come home. It is the ultimate one-way mission. The data it sends back is the return. The spacecraft itself is a sacrificial messenger. From a navigation standpoint, Breakthrough Starshot is fascinating precisely because it strips the problem down to its absolute essentials. There is no crew to navigate, there is no return journey to plan. The navigation challenge is simply this: aim accurately enough at launch that something interesting happens at the destination, and then receive and decode the resulting signal. And even that stripped-down challenge, aim, wait 20 years, receive, runs into profound practical difficulties that the research community is still working to address. The second category of serious interstellar mission proposals involves nuclear propulsion, specifically nuclear pulse propulsion. This is an older idea than Breakthrough Starshot, developed in a very different era, and one that has a somewhat dramatic history. In the 1950s and 60s, a group of physicists at General Atomics, led by Ted Taylor and Freeman Dyson, worked on a concept called Project Orion. The idea was breathtaking in its audacity: propel a large spacecraft by detonating a series of nuclear bombs behind it. Each explosion would be absorbed by a massive pusher plate, a thick metal disc attached to the rear of the spacecraft by shock absorbers, which would transfer the impulse from the explosion into forward thrust for the spacecraft. With sufficient numbers of nuclear detonations, an Orion spacecraft could be accelerated to a substantial fraction of the speed of light. The physics worked. Dyson calculated that an Orion spacecraft, using thermonuclear bombs and with a mass of around 400,000 tons, could potentially reach speeds of approximately 3 to 5% of the speed of light, sufficient for a journey to Alpha Centauri in roughly 80 to 100 years. A more ambitious design, sometimes called the Orion battleship, using fusion bombs optimized for specific impulse, could potentially reach higher fractions. Dyson himself believed that a sufficiently large Orion spacecraft could reach 10% of light speed. Project Orion was cancelled in 1963, not because the physics didn't work, but because of the Partial Nuclear Test Ban Treaty, which prohibited nuclear detonations in space. The political and environmental reality of launching a spacecraft by exploding thousands of nuclear bombs in low Earth orbit, with the associated radioactive fallout, made the project untenable. Regardless of its technical merits, subsequent nuclear propulsion concepts have been less dramatic but more politically feasible. Nuclear thermal propulsion, using a nuclear reactor to heat propellant to extreme temperatures and expel it through a nozzle, has been studied extensively and offers roughly twice the efficiency of the best chemical rockets. NASA and DARPA have been actively developing nuclear thermal propulsion systems in recent years, with the Draco program aiming to demonstrate a nuclear thermal rocket engine in space by the late 2020s. Nuclear thermal propulsion could significantly reduce travel times within the solar system. A crewed Mars mission that currently faces a 6 to 9 month one-way transit with chemical rockets could potentially be completed in 3 to 4 months with nuclear thermal propulsion. But its exhaust velocity is far too low for interstellar travel. The speeds achievable with nuclear thermal propulsion, a few tens of kilometers per second, would make even the nearest star a journey of tens of thousands of years. Nuclear pulse propulsion in more refined forms, specifically a concept called Medusa, and variants of the Orion concept using inertial confinement fusion rather than fission bombs, offers more promise for interstellar scales. A concept called Project Daedalus, designed by the British Interplanetary Society in the 1970s, proposed using electron beam ignited deuterium helium-3 fusion pellets as the propulsion source. The Daedalus design would achieve around 12% of the speed of light, with a journey time to Barnard's star, a red dwarf roughly 6 light-years from Earth, of approximately 50 years. A more recent study called Project Icarus has revisited and refined the Daedalus design with updated physics and materials science. What does nuclear pulse propulsion look like from a navigation perspective? Better than breakthrough starshot in some respects, worse in others. A nuclear pulse propulsion spacecraft would be large, potentially thousands of tons, which means it could carry substantial onboard navigation systems, fuel for attitude control and minor trajectory corrections, and potentially a significant computing infrastructure for autonomous navigation. The slower speed compared to breakthrough starshot, 12% versus 20% of light speed, also means slightly more time for mid-course corrections, though the correction capability is still severely limited by the available propellant budget. The fundamental problems remain. Communication delays of years, no external reference frame for navigation. The expanding universe, the proper motions of stars, the uncertainty introduced by dark matter distributions, these don't go away because the spacecraft is larger or more capable. They are features of the cosmos, not of the spacecraft. And at 12% of light speed, special relativistic effects, while less extreme than at higher fractions, are still non-negligible. A 50-year journey to Barnard's star would be experienced as approximately 49.5 years aboard the spacecraft. The discrepancy is small but real, and it grows with speed and distance. Navigation over interstellar distances must account for this time dilation. The clocks aboard the spacecraft and the clocks on Earth will not agree, and the navigation calculations performed on Earth and transmitted to the spacecraft must account for the difference in elapsed time between frames of reference. There is also the question of fuel. The Daedalus design required 50,000 tons of helium-3 as fuel, an isotope that is vanishingly rare on Earth, present primarily in the lunar regolith in trace amounts deposited by the solar wind and available in larger quantities in the atmospheres of the outer planets. Obtaining 50,000 tons of helium-3 would require a mining operation of extraordinary scale, sustained over decades using technologies that don't yet exist. The fuel requirement is not a fundamental physical barrier the way the speed of light is, but it is an engineering and resource challenge that dwarfs anything humanity has yet undertaken. The third category of proposals is the one that intersects most directly with the video we've referenced throughout this script, the Generation ship. And I want to discuss it here in some depth because the Generation ship is in many ways the most honest approach to interstellar travel. It doesn't try to be clever about the physics, it doesn't propose exotic matter or warp bubbles or laser sail nanoprobes. It says, the distances are vast, the travel times are long, and the answer is to build a world that can sustain human life for the entire duration, across multiple generations. The navigation challenges facing a generation ship are different in character from those facing a fast probe, and in some ways more daunting, even though the timescales are more forgiving. A generation ship traveling at, say, 1% of the speed of light, achievable with plausible near-future nuclear propulsion, would take roughly 400 years to reach Alpha Centauri. At that speed, relativistic effects are tiny. The ship's clocks and Earth's clocks would disagree by only a fraction of a percent. The navigation problem is not one of relativistic time dilation. It is one of sustained accuracy over an enormously long timescale. 400 years is a long time for anything to drift. Inertial navigation systems accumulate errors continuously, tiny imperfections in accelerometer readings, each too small to matter individually, adding up over 4 centuries into positional uncertainties that could place the ship light hours or light days from the intended trajectory at the destination. The star field the navigation computer uses as its reference will change over 4 centuries. The proper motions of stars, at typical velocities of tens of kilometers per second, will shift their apparent positions by measurable angles over that timescale. The onboard star catalogue will need to anticipate and account for those motions. The pulsar timing data used for navigation will need to be corrected for the slowing of pulsar rotation rates over 4 centuries. The communication delay at 4 light-years distance will be 4 years each way for a round-trip signal, making real-time navigation support from Earth impossible and requiring the ship to be genuinely autonomous in its navigational decisions. And then there is the human dimension. 400 years is approximately 16 to 20 human generations. The people who land at Alpha Centauri, if everything goes right, will not be the people who left Earth. They will be the great-great-great-great-great-great-great-great-great-great-great-great-grandchildren of the original crew. They will have grown up on a spacecraft. They may never have seen a planet, a sky, an open horizon. Their entire concept of place, of home, of where they are and where they're going, will have been shaped by the interior of a vessel that is, by any human standard, extraordinarily confined. How do you maintain navigational knowledge and navigational purpose across 16 generations? How do you ensure that the people born in Generation 7 or Generation 12 still understand why they are going, where they're going, still maintain the technical skills to operate the navigation systems, still care about the destination rather than the ship becoming, de facto, the only home anyone has ever known? These are not engineering problems, they are civilizational problems. They are the kinds of problems that historians, sociologists, and anthropologists study in the context of how human societies maintain knowledge and purpose over long timescales, and the historical record is not uniformly encouraging. The library at Alexandria was destroyed. The Roman engineering knowledge required to build the Pantheon was lost after the fall of the Western Empire and not recovered for over 1,000 years. The navigational traditions of the Polynesian peoples, arguably the most sophisticated open ocean navigation system ever developed by pre-industrial humans, came close to being lost under colonial pressure and were only partially reconstructed in the late 20th century through deliberate cultural revival efforts. Maintaining complex technical knowledge over centuries without external inputs in a closed and isolated community is one of the hardest challenges in human history, and a generation ship would face that challenge in perhaps its most extreme form. The navigation problem on a generation ship is not just a physics problem, it is a culture problem, a memory problem, a civilization in miniature problem. And the solution, if there is one, probably requires not just better gyroscopes and better star catalogues, but better institutions, better traditions, better ways of transmitting knowledge and purpose across generations. the same tools that human societies have always used to pass understanding from one generation to the next. Education, ritual, story, art, the careful cultivation of shared identity and shared purpose become, on a generation ship, tools of literal survival. There is a concept in navigation theory that I want to introduce here, because I think it captures something essential about the generation ship problem and about the deep space navigation problem more broadly. It is called dead reckoning. Dead reckoning is one of the oldest navigation techniques in human history. The name derives most likely from the abbreviation DEAD, short for deduced reckoning. The principle is simple. If you know where you started, you know how fast you're going, and you know what direction you're traveling in, you can calculate where you are now, even without any external reference points. You don't need to see the stars or the shore. You just need to track your speed and heading and time and keep updating your position estimate accordingly. Dead reckoning was the primary navigation method used by Polynesian navigators, by European ocean voyagers before the chronometer, and by submarines operating below the surface. It works. Over short distances and timescales, it works remarkably well, but it has a fundamental vulnerability. Error accumulates. Every small uncertainty in your speed, heading, or time, every tiny miscalibration of your instruments, every unexpected current or wind or gravitational perturbation compounds. The further you travel, the more your dead-reckoned position diverges from your true position. Without periodic external fixes, without a landmark, a star site, a GPS signal, a pulsar timing measurement, the error grows without bound. A generation ship navigating by dead reckoning across 400 years and 4 light-years of space would accumulate positional errors that are, by the end of the journey, very difficult to bound without external references. The pulsars help, the star catalogue helps, but both of those external references are themselves uncertain. The pulsars slow down in ways that are imperfectly modelled, and the proper motions of stars are measured with finite precision. The dead reckoning is always running. The question is only how well it can be corrected along the way. This is, in a very real sense, the human condition. We are all dead reckoning through time. We started somewhere, in a particular culture, a particular family, a particular body, a particular historical moment, and we are tracking our speed and heading as best we can, accumulating errors, correcting occasionally when a landmark appears, doing our best to know where we are and where we're going. The navigation problem of the generation ship is not alien to us. It is a vast technological, interstellar version of something we do every day. As individuals and as civilizations, the question is not whether we can eliminate the error. We can't. The question is whether we can manage it, catch it before it grows too large, correct it with the best available external references, and maintain enough situational awareness to arrive somewhere close enough to where we intended to go, that the journey retains its meaning. I want to close this part by returning to a question that has been hovering over this entire conversation, and that the generation ship brings into its sharpest possible focus: the question of what home actually is. For the crew of a generation ship, particularly the later generations who have known nothing but the ship, home is the ship. Not Earth, which is a story their great-grandparents told. Not Alpha Centauri, which is a destination they've been taught about but have never seen. The ship itself, its corridors and gardens and workshops and sleeping quarters and observation decks and kitchens, is home. The community aboard it is home. The shared purpose of the mission, transmitted imperfectly but earnestly across generations, is home when that ship finally arrives at Alpha Centauri. If it arrives, if the navigation has been accurate enough, if the systems have held together, if the knowledge has been preserved, the people aboard will be facing a planet or a star system they've been told is their destination, but that, experientially, is entirely alien to them. The planet is not home. The ship is home, and the prospect of leaving the ship, of descending through an alien atmosphere to stand on an alien surface, surrounded by alien light from an alien star, might be far more psychologically complex and disorienting than the original designers of the mission anticipated. And what about Earth? Earth is 4 light years away. 4 years for a signal to arrive, 8 years for a question and an answer. The people who launched the mission are dead. Their children are probably dead. The civilization that built the ship has had 400 years to change, possibly to advance beyond recognition, possibly to collapse, possibly to have sent other ships that arrived before them by faster means not yet invented when they left. The Earth they return to, if they return at all, is not the Earth they came from. In every meaningful sense, they cannot go home, because home was a moment in time, not just a place in space, and that moment is 400 years gone. This is perhaps the deepest navigation problem of all. Not the technical challenge of knowing where you are in space, but the existential challenge of knowing where you are in time. Of understanding that the universe does not hold still while you travel through it. Of accepting that the home you left is, in a very real sense, already gone, and that whatever you find at the end of the journey, it will be something new, something you will have to build rather than find, something that will require not just navigation but creation. The universe is not a fixed landscape with a home address you can return to if you just get the coordinates right. It is a dynamic, evolving, expanding, changing process, and you are part of that process. You are not traveling through the universe. You are part of it, moving with it, changed by it as it is changed by you. Finding your way home in deep space is not a problem of knowing your coordinates. It is a problem of understanding what home means when the cosmos is your context. And that is a problem that no instrument, no algorithm, no map, however precise, can solve on its own. It requires something the instruments don't have and can't be given. It requires wisdom. If you are still watching, please subscribe to the channel and give this video a like. Every video we put out is built to expand your thinking and leave you seeing the world differently. There is a moment in the history of every great human endeavor where the question shifts, where it stops being, can we do this, and starts being, what kind of people do we need to be to do this? The Apollo program reached that moment not in the engineering rooms at NASA, but in the years after the program ended, when the world realized that the thing it had built and then dismantled was not just a rocket and a capsule and a lunar module. It was a civilizational capacity, a way of organizing human knowledge and human will and human resources toward an almost impossibly ambitious goal. And that capacity, once lost, took decades to begin rebuilding. Deep space navigation is not primarily a technical problem waiting for a technical solution. It is a civilizational challenge. It requires not just better instruments and better algorithms and better propulsion systems, though it requires all of those things in abundance. It requires a particular kind of long-term thinking, a particular kind of institutional patience, a particular kind of scientific culture that is genuinely difficult for any human society to sustain across the timescales the problem demands. Not years, not decades, centuries, possibly millennia. This part is about what it would actually take as a species, as a civilization, as a community of minds to genuinely solve the deep space navigation problem, to get from where we are now, which is the extraordinary and humbling position of being able to navigate within our own solar system with impressive precision, but having essentially no capability to navigate beyond it, to a place where a spacecraft can leave our solar system, travel to another star, and find its way home with genuine confidence. The answer involves physics we haven't discovered yet, mathematics we haven't invented yet, technologies we haven't built yet, and perhaps most importantly, a relationship with time that is fundamentally different from the one that governs almost every decision made by every institution on Earth today. Let me take you through it carefully. The first thing that needs to happen, and this is not optional, it is the foundation upon which everything else rests, is a resolution of the tension between quantum mechanics and general relativity. A theory of quantum gravity, I mentioned this in part 7, and I want to return to it here with more specificity about why it matters for navigation, because the connection might not be obvious. Quantum gravity operates at the Planck scale, distances of 10 to the minus 35 meters, energies of 10 to the 19th gigaelectronvolts. These scales are so far removed from the scale of a spacecraft or a star system that they might seem irrelevant to anything practical, but they are not irrelevant. They are foundational. Here is why. Every measurement we make of the universe, every observation of a pulsar, every triangulation using starlight, every gravitational wave detection, every mapping of the cosmic microwave background is ultimately an act of quantum measurement. The photons we detect, the signals we process, the instruments we use to detect them, are all governed by quantum mechanics, and the space-time through which those photons travel, in which those signals propagate, in which those instruments sit, is governed by general relativity. A complete, consistent theory of how these two frameworks fit together would tell us, with mathematical rigor, the ultimate limits of what can be measured, the fundamental precision boundaries that no instrument, however well designed, can ever surpass. Right now, we don't know those limits with confidence. We have estimates based on the uncertainty principle, on the Planck scale, on semi-classical approximations, but we don't have a complete picture. A theory of quantum gravity would give us that picture. It would tell us exactly how precisely position, velocity, and direction can be measured in a universe where space-time itself is quantized. It would tell us whether the granularity of space-time at the Planck scale has any observable effects at navigational scales, whether, at some level of precision, the quantum foam of space-time introduces irreducible noise into position measurements. It would tell us whether the holographic principle, in its full form, provides a practical encoding of spatial information that could be exploited for navigation, or whether that encoding is so deeply buried in quantum correlations that it is, for practical purposes, inaccessible. These are not academic questions. They are the questions that determine the ceiling of what is achievable, and until we know the ceiling, we cannot know how close we are to it. A theory of quantum gravity has been the central unsolved problem in theoretical physics for nearly a century. It may remain unsolved for another century. It may require experimental data that current technology cannot provide, data from near a black hole singularity, or from the first instance of the Big Bang, or from phenomena at energies that no particle accelerator could ever reach. It may require conceptual breakthroughs of a kind that cannot be planned or scheduled or funded into existence. It may require a mind we haven't produced yet, a Newton or an Einstein of the 22nd or 23rd century, working with mathematical tools that haven't been invented and observational data that hasn't been collected, but it is the foundation. Without it, everything else we build for deep space navigation sits on ground we haven't fully surveyed. The second thing that needs to happen is a dramatic improvement in our map of the universe, particularly our understanding of dark matter and dark energy. I've discussed both of these throughout this script, but let me be specific here about what improvements are needed and why they matter for navigation. Dark matter constitutes approximately 27% of the universe's total energy content, and its distribution shapes the gravitational landscape through which any spacecraft must travel. Right now, our knowledge of the dark matter distribution is statistical. We know roughly how much dark matter there is. and we have maps of its large-scale distribution from gravitational lensing surveys and galaxy clustering measurements. But we don't know what dark matter actually is. We don't know whether it is a single particle or multiple particles. We don't know whether it interacts with ordinary matter in any way other than gravity. We don't know whether its distribution is smooth or clumpy at small scales. All of these unknowns translate directly into navigational uncertainty. A spacecraft traveling from our solar system to another star is moving through a gravitational landscape partly shaped by dark matter, distributed in ways we cannot directly observe. The effect on a single trajectory over a few light years is small, the dark matter density in our local neighborhood is low, and the gravitational perturbations over short interstellar distances are modest. But they are not zero, and over longer distances or in regions of higher dark matter density, near the galactic center, for example, or in galaxy clusters, the navigational effects of poorly mapped dark matter become significant. The situation with dark energy is even more fundamental. Dark energy, whatever it is causing the expansion of the universe to accelerate. That acceleration is changing the relationship between distance and redshift, between position and signal travel time, in ways that affect every measurement we make of the distant universe. The Hubble tension, the persistent, statistically significant disagreement between different measurements of the universe's current expansion rate, tells us that our current model of dark energy is not complete. Something is missing, and what's missing affects our ability to accurately measure distances at cosmological scales, which is precisely the scale at which deep space navigation becomes most challenging. The next generation of observational facilities will help enormously. The Vera C. Rubin Observatory in Chile, which began full science operations in 2025, will conduct the legacy survey of space and time, scanning the entire southern sky repeatedly over 10 years, mapping billions of galaxies and producing the most comprehensive survey of the large-scale structure of the universe ever assembled. The Nancy Grace Roman Space Telescope, planned for launch in the late 2020s, will conduct wide-field infrared surveys that will dramatically improve constraints on dark energy. The Euclid satellite, launched in 2023, is already mapping the geometry of the universe using galaxy clustering and weak gravitational lensing across billions of light years. These instruments will not solve the dark matter and dark energy problems overnight, but they will provide the data from which solutions can eventually be constructed. And each improvement in our map of the universe's dark sector is an improvement in the accuracy with which any deep space navigator could understand the gravitational landscape they're moving through. The third requirement is technological, and it is both specific and ambitious. We need quantum sensors of a quality and stability that fundamentally surpasses anything currently achievable. And we need them to work autonomously over decades in the harsh environment of deep space. Let me explain what I mean by quantum sensors in this context, because the term can mean different things in different fields. The navigation challenge in deep space is fundamentally a measurement challenge, measuring the positions and velocities of stars, the timing of pulsar signals, the gradients of the local gravitational field, and the orientation of the spacecraft with the highest possible precision, using the lowest possible power with the highest possible reliability over the longest possible timescale. Quantum sensing refers to the use of quantum mechanical phenomena, quantum superposition, quantum entanglement, quantum coherence, to achieve measurement precisions that are fundamentally impossible with classical instruments. Quantum gravimeters, for example, use clouds of ultra-cold atoms in quantum superposition states to measure gravitational field gradients with extraordinary sensitivity. The atoms, cooled to near absolute zero, and held in specific quantum states, act as exquisitely sensitive probes of the local gravitational environment. Quantum gravimeters operating today in laboratory settings can detect gravitational changes corresponding to height differences of centimeters, sensitive enough to detect the gravitational signature of an underground aquifer or a void in bedrock. In principle, a sufficiently sensitive quantum gravimeter aboard a deep space spacecraft could map the gravitational landscape of a stellar system with enough precision to provide accurate positional information without relying on optical measurements or electromagnetic signals. Quantum gyroscopes, using atom interferometry, the same principles as quantum gravimeters, but oriented to measure rotation rather than linear acceleration, can achieve angular measurement precisions far beyond classical gyroscopes. They do not drift in the way mechanical gyroscopes do. Their precision is limited by quantum mechanical noise flaws rather than mechanical imperfections, which means their accuracy can be improved, in principle, by using more atoms and longer interaction times. A quantum gyroscope accurate enough to track orientation over a multi-decade deep space mission without accumulating significant drift would be transformative for inertial navigation. Optical atomic clocks, already operating in laboratories with a precision of roughly 1 second in 30 billion years, provide the timing accuracy that pulsar navigation requires. Getting atomic clocks of this precision into a radiation-hardened, deep space-capable form factor powered by a feasible power source over a mission lifetime of decades is an engineering challenge that is immense but not fundamentally impossible. The physics is known, the engineering is hard, and quantum communication using quantum entanglement to transmit quantum states between the spacecraft and Earth would not allow faster-than-light communication, as we discussed in Part 6. But it would allow communication that is, in principle, immune to interception and eavesdropping, and that can be used for certain quantum-enhanced measurement protocols. More relevantly for navigation, advances in quantum communication technology drive advances in the underlying quantum optics and photon detection capabilities that are directly useful for optical navigation, detecting faint starlight, measuring stellar parallax and proper motion, and eventually perhaps detecting the gravitational wave background as a navigational reference. The timeline for these technologies, for quantum sensors capable of meeting the deep space navigation challenge, is probably measured in decades, not years. The laboratory demonstrations are already extraordinary. The engineering translation to a deep space platform is where the hard work lies. But the trajectory is clear and the progress is real. The fourth requirement is the one that I think is most underappreciated, most underdiscussed, and most likely to be the actual limiting factor. Not the physics, not the technology, not even the funding. It is institutional. It is the capacity to sustain a scientific and engineering program across timescales that no current human institution is designed to handle. Think about what deep space navigation actually requires temporally. The breakthrough Starshot concept, if it were funded and developed today, would launch its first star chips in perhaps 20 to 30 years. Those probes would reach Alpha Centauri in another 20 years. The data would arrive on Earth 40 years from now, long after everyone involved in the current research program has retired or died. The navigation systems being designed today would be operating in 40 years in a technological and scientific context that is completely unpredictable from our current vantage point. A generation ship mission would be planned over decades, built over decades, launched, and then not arrive at its destination for 400 years. The institution that launches it must somehow maintain relevance, authority, and capability for those 400 years in a world that has no precedent for this kind of commitment. It must continue to receive the ship's signals, process its data, provide navigational support across 8-year round-trip communication delays, and keep alive the knowledge and motivation needed to assist the crew through problems that haven't been anticipated. No human institution has ever successfully sustained a single-focused technical program for 400 years. The oldest universities, Bologna, Oxford, Cambridge, are approximately 900 years old, but they have changed beyond all recognition over that period in their structure, their purpose, their knowledge base, and their institutional culture. The Catholic Church is approximately 2,000 years old as an institution, but its technical programs, such as they have been, have not required continuous, uninterrupted, specialized engineering capability. The Roman aqueducts were built over centuries, but represented accumulated knowledge passed down through practical apprenticeship, not the kind of complex precision engineering that deep space navigation requires. What kind of institution could sustain a generation ship mission? What legal structures? What funding mechanisms? What governance arrangements? What cultural practices would be needed to ensure that an organization founded in, say, 2050 continues to maintain both the capability and the mandate to receive and process signals from a spacecraft launched in 2080, arriving at its destination in 2480? This is not a question that engineers or physicists are well equipped to answer. It is a question for political scientists, historians, legal scholars, anthropologists, and institutional designers, and it is a question that the deep space navigation community has barely begun to take seriously. There are historical precedents for very long-term institutional commitments that might be instructive. The reforestation programs of medieval European nobility, where forests were planted with the explicit expectation that the timber would not be harvested for 200 years and the benefit would accrue to descendants many generations removed. The construction of great cathedrals, which took decades or centuries to complete, requiring the transmission of specialized craft knowledge through generations of workers who would never see the finished structure. The maintenance of lighthouse systems, which required sustained institutional commitment to keep lights burning and warning signals operational across generations. None of these is an exact model for a generation ship support organization, but they illustrate that humans are not entirely incapable of thinking and acting across generational timescales. The challenge is that the modern world, with its quarterly earnings reports, its 4-year political cycles, its venture capital timelines, its social media news cycles, has systematically optimized institutions for short-term returns at the expense of long-term capacity. Rebuilding the institutional muscles needed for multi-generational commitments is not just a matter of will. It requires structural changes to how we organize collective endeavor, changes that are as challenging in their domain as any of the physics or engineering problems we've discussed. The fifth requirement brings us back to something I raised at the very beginning of this journey, in the very first part of this script, and that has been running underneath every subsequent discussion like a quiet river under a city. It is the question of the reference frame, the home base, the thing you are navigating from and navigating back to. Every navigation system requires an anchor, a fixed point, or as close to fixed as you can get, relative to which all other positions are defined. On Earth, we use the planet itself as our reference frame. In the solar system, we use the solar system barycentre, the center of mass of the entire solar system, which itself moves around the Milky Way, but which provides a stable local reference for solar system navigation. For deep space navigation beyond the solar system, the question of what to use as an anchor becomes genuinely profound. The Milky Way itself moves relative to other galaxies, relative to the local group's barycentre, relative to the Virgo supercluster, relative to the Great Attractor, relative to the cosmic microwave background. Every reference frame is itself moving relative to some larger reference frame. At the very largest scale, the only truly universal reference frame we have is the cosmic microwave background, the afterglow of the Big Bang, filling the entire observable universe with extraordinary uniformity, providing a reference frame in which motion can be measured by the Doppler shift it induces in the CMB temperature. A spacecraft navigating at interstellar or intergalactic scales would need to use the CMB as its ultimate reference frame. And the CMB is accessible, it fills all of space, it comes from all directions, and a spacecraft with a sufficiently sensitive microwave detector can measure its direction and temperature distribution and therefore determine its velocity relative to the CMB rest frame. This is not hypothetical. The COBE, WMAP, and Planck satellites have all measured the CMB dipole, the asymmetry in CMB temperature caused by Earth's motion through the CMB rest frame, with great precision, determining that the solar system is moving at approximately 370 kilometers per second relative to the CMB rest frame in the direction of the constellation Leo. In principle, a CMB-based navigation system using the CMB temperature distribution as a fixed reference could provide orientation and velocity information anywhere in the observable universe. The CMB is the same everywhere. It is the most universal reference frame available, and it is accessible to any spacecraft with appropriate instruments without requiring communication with Earth or any external infrastructure. The limitations of CMB navigation are real but not insurmountable in principle. The CMB is highly uniform. Deviations from perfect isotropy beyond the dipole are at the level of 1 part in 100,000. Using those tiny temperature fluctuations as navigational landmarks requires instruments of extraordinary sensitivity. The CMB fluctuations are also on very large angular scales. The features in the CMB are tens of degrees across, not arcseconds, which limits the precision with which they can be used to determine orientation. And the CMB is a snapshot of the universe as it was 380,000 years after the Big Bang. It doesn't encode any information about the current positions of stars, galaxies, or other navigational landmarks, but as an absolute orientation reference, a way of determining which direction you're pointing relative to the universe as a whole. The CMB is unmatched, and combined with pulsar timing for precise velocity and position measurement, and optical star tracking for short-range positional fixes, a CMB and chord navigation system begins to look like a genuinely viable framework for deep space navigation, not perfect, not free from uncertainty, but far better than anything we currently have. The sixth requirement, and I've saved this one for near the end deliberately, because it is the one that is simultaneously the most important and the most difficult to quantify, is a shift in how we think about the relationship between knowing where you are and deciding to go anyway. Throughout this entire script, we have been approaching the navigation problem from a particular angle. We've been asking, how do you know where you are? How do you find your way home? How do you maintain positional certainty across the vast distances and long timescales of interstellar travel? And implicit in all of those questions is an assumption that certainty is required, that you need to know where you are before you can proceed. That navigation is a prerequisite for travel, but the history of human exploration suggests something more complicated and more interesting. The people who crossed the Pacific in outrigger canoes did not know with precision where the next island was. They had deep knowledge of the stars, the swells, the winds, the birds, and the clouds, but their knowledge was probabilistic, embodied, experiential. It was not the kind of knowledge that could be written down as coordinates and verified against a chart. They navigated by attending to the universe with extraordinary sensitivity, and moving toward where the evidence suggested land might be. They went and they found, not always, not without loss, but often enough and well enough that they populated an ocean. The European navigators of the 15th and 16th centuries who crossed the Atlantic did not know what was on the other side. Columbus thought he was going to Asia. He was wrong, but he went anyway, and the process of going, of being actually present in the unknown ocean, experiencing it directly, learning from it in real time, was what generated the knowledge that subsequent navigators could use. Navigation improved not by theorizing about the ocean from a safe harbor, but by crossing it, getting lost in it, and finding ways to continue anyway. This is not an argument for recklessness. It is not a suggestion that we launch interstellar missions before we've developed adequate navigation systems and hope everything works out. The stakes of interstellar travel, the enormous resources required, the human lives potentially at risk, the impossibility of rescue, demand the most rigorous possible preparation. But there is a deep truth embedded in the history of exploration that is relevant here. The act of going generates knowledge that no amount of prior theorizing can fully substitute for. The first crewed mission to Mars will teach us things about deep space navigation that all our simulations and models cannot fully anticipate. The first automated probe to Alpha Centauri, whether it's a Starshot nanoprobe or something else, will provide navigational data of a kind and quality that will transform our understanding. The first generation ship, if one is ever launched, will be an experiment as much as a mission, and the knowledge gained from it, transmitted back across the light years, will shape everything that comes after. The shift in thinking required is this: navigation does not need to be perfect before departure. It needs to be good enough, combined with enough redundancy, enough autonomy, enough adaptability, and enough humility about what is not yet known, that the mission can survive the inevitable surprises and continue to generate useful information. The goal is not to eliminate uncertainty before going. The goal is to go in a way that manages uncertainty intelligently and turns the experience of navigating into a source of knowledge that makes the next journey more successful than the current one. This is how science itself works, not by achieving certainty before acting, but by acting carefully and learning from what happens, iterating toward better understanding with each experiment. Deep space navigation is, in this sense, an extension of the scientific method into the cosmos itself. Each mission is an experiment, each trajectory is a hypothesis, each arrival or failure to arrive is data. Let me bring all of this together now, because we are approaching the end of this journey, and I want to make sure we've been honest, genuinely, unflinchingly honest, about what the deep space navigation problem is and what it would take to solve it. Here is the honest summary. The deep space navigation problem is not one problem. It is a nested hierarchy of problems at different levels of fundamental depth. At the deepest level, it is a problem of incomplete physics. We do not yet have a theory of quantum gravity. We do not yet understand dark matter and dark energy, and our map of the universe's structure is therefore incomplete in ways that matter for navigation. At the next level, it is a problem of measurement. Our current instruments cannot achieve the precision needed for interstellar navigation over meaningful timescales, and the quantum sensors that might eventually achieve that precision are still decades from being ready for deep space deployment. At the next level, it is a problem of communication. The finite speed of light imposes irreducible delays that make real-time navigation support from Earth impossible over interstellar distances, requiring spacecraft to be genuinely autonomous in ways that current artificial intelligence cannot reliably provide over multi-decade mission lifetimes. At the next level, it is a problem of institutions. No human organization currently exists or has ever existed with the structure and mandate and cultural practices needed to sustain a deep space navigation program across the centuries that interstellar travel requires. And at the deepest human level, it is a problem of meaning, of understanding what home is, what return means, and whether the concept of finding your way back makes sense in a universe that is always moving, always changing, and always larger than any map we've yet made of it. None of these problems is unsolvable. I want to be clear about that. I have not been building toward a conclusion of despair or defeat. The history of science is a history of problems that seemed permanently impossible, yielding to sustained, creative, rigorous effort applied across generations. The navigation problem is hard, genuinely, profoundly hard at every level from quantum gravity to institutional design, but hard is not the same as impossible. And the fact that the universe is comprehensible at all, the fact that the same mathematics works here, and at the edge of the observable universe, the fact that the laws of physics are the same in every direction we've looked, the fact that we can read the composition of a star billions of light years away from the fingerprints it leaves in its light, suggests that the universe is, at some fundamental level, on our side. It is knowable. It is navigable in principle, even when it is not yet navigable in practice. The path from where we are to where we need to be is long. It will require discoveries we cannot yet anticipate. It will require institutions we haven't yet built. It will require generations of scientists and engineers and philosophers and explorers who haven't yet been born. And it will require, at every step of the way, the same quality of mind that has brought us from a species that looked up at the stars in wonder to a species that has sent its machines to the edge of the solar system and its eyes to the beginning of time. Curiosity, rigor, humility, patience, and the deep, persistent, specifically human conviction that the unknown is not something to be feared, but something to be understood. There is something I want to leave you with before we go to the final part of this script. Something that I think gets to the heart of why the deep space navigation problem matters beyond its immediate practical significance. We are, right now, in the early moments of becoming a spacefaring species. Not fully spacefaring, we have not yet left our own solar system with a crewed mission, and we are many decades at least from doing so. But the trajectory is clear. We have landed on the Moon. We have sent robots to Mars, Venus, Jupiter, Saturn, Uranus, Neptune, and the edge of the solar system. We have put telescopes in orbit that have shown us the structure of the universe from its first light to the present day. We have detected gravitational waves, directly imaged black holes, and mapped the cosmic web. We are building the tools for the next step. The navigation problem is not a barrier to that step. It is the shape of the step. It is what the step requires. Solving it, or making enough progress on it to begin, is not separate from becoming a spacefaring species. It is what becoming a spacefaring species means. And there is something deeply right about the fact that the hardest part of going to the stars is not the propulsion, not the life support, not the communication, but the navigation, the knowing where you are, the understanding of your place in the cosmos. Because that understanding, the genuine, mathematically rigorous, observationally grounded understanding of where you are in the universe, is also one of the deepest products of science itself. Navigating the cosmos and understanding the cosmos are not different activities. They are the same activity at different scales. To know where you are in the universe is to understand the universe, and to understand the universe is the oldest and most human of all ambitions. We are working on it, so here is the truth that this entire journey has been building toward. The reason it is impossible to find your way home in deep space is not a failure of our technology, or our mathematics, or our courage. It is a consequence of the most profound fact about the universe there is, that it is always moving, always expanding, always becoming something it has never been before, and so are you. The you that left is not the you that arrives. The home you departed is not the home you return to. The stars you navigate by are showing you their past, not their present. The universe does not hold still, and neither do you, and that is not a tragedy. That is the condition of being alive in a cosmos that is itself alive with change, with motion, with the restless, magnificent process of becoming. You are made of atoms forged in the cores of stars that died before the sun existed. You are literally the universe finding a way to look at itself and ask, where am I? Where am I going? And how do I find my way back? The fact that those questions are so hard to answer is not a sign that we are lost. It is a sign that the universe is so much larger, so much richer, and so much more extraordinary than any map we could ever make of it. And perhaps that is exactly the point. Perhaps the journey was never really about coming home. Perhaps it was always about learning, in the deepest possible way, what home actually is. If everything we just covered made you wonder whether humans could even survive the journey in the first place, that video is already on your screen. We explore how long would we survive interstellar travel. Click it now. Trust me, after everything you just learned, you need to see this one.